Welcome to a peaceful journey through the physics of planetary atmospheres, from Venus's greenhouse to Titan's methane lakes. Tonight, I invite you to join me on a gentle voyage through some of the most fascinating aspects of our universe. As you settle in and close your eyes, imagine yourself floating weightlessly in the vast expanse of space, surrounded by the gentle glow of distant stars. We're going to explore 22 interconnected aspects of the physics of planetary atmospheres, from Venus's greenhouse to Titan's methane lakes, each flowing naturally into the next, like celestial bodies in their eternal, peaceful dance. Let yourself relax as we drift together through these cosmic wonders. Imagine, for a moment, simply breathing. Feel the gentle, invisible presence of the air around you. It surrounds us, sustains us. Yet we rarely pause to truly consider this wondrous, ethereal envelope that embraces our entire world. This protective veil of gas, known as an atmosphere, is far more than just the air we breathe. It is a fundamental, defining characteristic of nearly every celestial body in our cosmos, a silent storyteller of a planet's very essence. Our journey through the physics of planetary atmospheres begins with this fundamental question: what truly defines an atmosphere? At its most basic, an atmosphere is a layer of gases held in place by a world's gravitational pull. Picture a vast cosmic hand, gently yet firmly holding countless tiny gas molecules close to a planet's surface, preventing them from drifting off into the cold, boundless vacuum of space. Without this steady, unwavering gravitational tug, these delicate gases would simply dissipate, leaving a barren, airless landscape behind. Consider the smallest constituents of this air, individual gas molecules. Each one is in constant random motion, vibrating and zipping about. On a planet without sufficient gravity, these tiny particles, given enough energy from sunlight or internal heat, would easily achieve what we call escape velocity, simply floating away, never to return. But gravity acts as an invisible anchor, continuously pulling these molecules back, creating a delicate balance that allows the atmosphere to persist, to form a continuous, cohesive blanket around its world. It is a quiet, ceaseless dance between the kinetic energy of the gas and the persistent pull of gravity, a foundational physics lesson playing out on a cosmic scale. But where, precisely, does this atmospheric blanket end and the vast emptiness of space truly begin? It is not a sharp, distinct line like the edge of a blanket neatly folded. Instead, it is a gradual, serene transition, much like the slow fading of a distant mist into the clear morning sky. As we ascend from a planet's surface, the air thins progressively, becoming less dense, less substantial, until individual gas molecules are so far apart that collisions between them become rare events. This region, where the atmosphere effectively blends into the vacuum, is often referred to as the exosphere, a zone where molecules can effectively escape into the void. For practical purposes, for the engineers and mission planners who design spacecraft, there are indeed conventional boundaries, like the Kármán line, often set at 100 kilometers above Earth. Above this altitude, the air is so thin that conventional aircraft can no longer generate lift, and orbital mechanics begin to fully dominate. But even above this imaginary line, a tenuous whisper of an atmosphere still exists, a ghost of the denser air below, gently fading into the ultimate quietude of interplanetary space. It reminds us that nature rarely draws sharp lines, preferring instead the grace of a slow, harmonious blend. Beyond simply holding gas molecules, an atmosphere serves as an extraordinary protective shield for the world it embraces. Think of the harsh conditions of space, the relentless, charged particles of the solar wind, the energetic bursts of cosmic rays, and the countless tiny fragments of rock and dust, micrometeoroids, silently zipping through the void. Without an atmosphere, these formidable threats would relentlessly bombard a planet's surface, sterilizing it, eroding it, and making any form of life incredibly difficult to sustain. Our own Earth's atmosphere, for instance, acts as a magnificent filter and deflector. It absorbs much of the harmful ultraviolet radiation from the sun, protecting delicate biological systems. It gently dissipates the energy of cosmic rays, reducing their impact on the surface. And perhaps most visibly, it performs a stunning celestial show almost every night, as countless meteors, often no larger than grains of sand, harmlessly burn up in a fiery streak through its upper layers, never reaching the ground. This atmospheric friction acts like a soft, invisible cushion, safeguarding the world below from constant bombardment. It also helps to regulate a planet's temperature, trapping warmth and preventing extreme fluctuations between scorching days and frigid nights, creating a more stable, peaceful environment. As we gently embark on this cosmic journey, we will discover that not all atmospheres are created equal. Far from it. Across our solar system, and indeed beyond to distant exoplanets, we encounter an astonishing diversity of these gaseous envelopes. Some worlds are cloaked in thick, crushing atmospheres that create searing infernos. Others possess atmospheres so thin they are barely detectable, offering little more than a whisper of gas before dissolving into space. There are atmospheres composed primarily of nitrogen, like our own Earth, or dense carbon dioxide, like our neighbor Venus, or even exotic methane and ethane, like the moon Titan. Each unique atmospheric composition, its density, its height, and its behavior, tells a profound story about the world it envelops. It speaks of its formation, its internal geological processes, its proximity to its star, and its very capacity to host life. From the dense, swirling cloud bands of the gas giants to the tenuous, escaping gases of icy moons, every atmosphere is a testament to the elegant, intricate physics that shapes our universe. This initial exploration of what defines an atmosphere is merely the first, serene step into understanding these magnificent, invisible structures, inviting us to contemplate the incredible variety and profound significance of the air that graces each world in the silent expanse of space. As we drift deeper into our exploration, cosmic ingredients, how atmospheres were born. We just contemplated the gentle embrace of an atmosphere, its silent presence defining and protecting a world. Now, let us drift back through the immense stretches of cosmic time to the very genesis of these ethereal blankets. We will explore how atmospheres were born, uncovering the serene, powerful processes that breathed life into these celestial envelopes, shaping the destinies of planets and moons across the universe. The story of an atmosphere often begins with the birth of its star, within a vast, swirling cloud of gas and dust known as a protoplanetary disk. Picture this disk as a slow-motion cosmic dance, with countless particles gradually clumping together, drawn by gravity's invisible hand. For the giant planets of our solar system, worlds like Jupiter and Saturn, their atmospheres are truly primordial. They represent the first way an atmosphere can form, by directly capturing vast quantities of the original, lightest gases from this very disk. As these colossal worlds grew, their immense gravitational fields became powerful enough to pull in and hold onto the abundant hydrogen and helium that comprised the vast majority of the early solar nebula. It was a process of slow, steady accumulation, like a cosmic sponge soaking up the surrounding mist. These nascent gas giants became enormous reservoirs of these primordial elements, forming the deep, expansive atmospheres we observe today. Imagine these behemoths quietly drawing in the very essence of their birthplace, forming an incredibly deep, enveloping ocean of gas. However, for the smaller, rocky planets closer to their star, like Earth, Venus and Mars, the story of atmospheric birth is quite different. These worlds were too small and too warm in their early stages to retain the light, fast-moving primordial hydrogen and helium. These early gases simply evaporated away, escaping into space. So, rocky planets had to generate their atmospheres anew, in a process known as outgassing, creating what we call secondary atmospheres. This is where the ancient, powerful forces hidden within a planet's interior come into play. Picture the molten heart of a young, still-forming world, churning with immense heat and pressure. Deep within this fiery core and mantle, certain volatile gases, like water vapor, carbon dioxide, nitrogen, and sulfur compounds, were trapped, embedded within the cooling rock as the planet slowly solidified. As the planet continued to evolve and its internal heat drove widespread volcanic activity, these trapped gases found their escape. Imagine vast volcanic eruptions, not as chaotic bursts, but as steady, powerful exhalations from the planet itself. Over millions of years, these ancient volcanoes continuously vented steam, carbon dioxide, and other gases into the nascent skies. Each gentle plume added its invisible contribution, slowly building up the first substantial envelopes of air around these rocky worlds. It was a slow, persistent breathing out by the planet, a geological process unfolding over immense timescales, gradually transforming barren rock into a world with air. This process of outgassing is a beautiful testament to the dynamic, living nature of planets, revealing how even seemingly inert rock can give rise to the very air we breathe. But the formation of an atmosphere is not a one-time event fixed forever. It is a continuous, dynamic dance with the surrounding cosmic environment, and sometimes atmospheres can gently be stripped away. This atmospheric escape is the counterpart to atmospheric birth, a process by which gas molecules slowly but relentlessly depart a planet, drifting off into the silent vacuum of space. One primary mechanism for this gentle loss is what we call thermal escape, or Jeans escape. Remember how gas molecules are constantly in motion? Well, if a molecule is light enough and moving fast enough, perhaps having gained extra energy from a collision or from solar radiation, it can eventually reach a speed that allows it to overcome the planet's gravitational pull entirely. Like a tiny, energetic bird finally lifting off from its nest, it simply floats away, never to return. This process preferentially affects lighter gases, like hydrogen and helium, which is why rocky planets initially lost most of their primordial atmospheres, and why even today, Earth slowly loses tiny amounts of these light elements from its upper atmosphere. Beyond this subtle thermal drifting, the Sun itself can act as a quiet, powerful sculptor, gently eroding planetary atmospheres over cosmic eons. Our Sun, like all stars, emits a constant stream of charged particles known as the solar wind. Imagine this solar wind as a soft, but persistent, cosmic breeze, flowing outward from the Sun at tremendous speeds. When this gentle yet energetic wind encounters a planetary atmosphere, especially one not shielded by a strong magnetic field, it can interact with the gas molecules in the upper layers. These interactions can impart enough energy to atmospheric particles for them to achieve escape velocity, slowly but surely carrying them away into space. This phenomenon, known as solar wind stripping, is believed to have played a significant role in shaping the atmospheres of worlds like Mars. Over billions of years, Mars, which lacks a global magnetic field, saw much of its once thicker atmosphere slowly but inexorably stripped away by this constant solar breeze, transforming it into the thin, cold environment we observe today. So, the birth of an atmosphere is a complex and fascinating story of cosmic ingredients and powerful, yet often serene, forces. From the quiet capture of primordial gases to the steady exhalation of volcanoes and the subtle, persistent erosion by solar winds, each world's atmosphere is a living testament to a long, gentle history of formation and change. This dynamic interplay means that the air surrounding any planet is not just a static blanket, but a constantly evolving story, a quiet reflection of its cosmic journey through time. Continuing our peaceful voyage through the universe, the invisible symphony, atmospheric composition. Imagine a grand, invisible symphony playing out around every world, a unique composition defined by the very air that envelops it. This cosmic music is not heard by our ears, but felt in the subtle interplay of light and warmth, shaped by the individual notes of various chemical elements. The precise blend of gases in an atmosphere is like a planet's unique signature, a quiet declaration of its history and its potential. We will now gently explore this invisible symphony, uncovering the common and rare ingredients that give each planetary atmosphere its distinct character. At the heart of this atmospheric composition are a few key players, gases that dominate the envelopes of worlds across our solar system. On Earth, our familiar atmosphere is predominantly composed of nitrogen. Picture nearly 4/5 of the air around you as this remarkably stable, relatively unreactive gas. Nitrogen acts like a quiet, reliable filler, providing the bulk of our atmospheric pressure without engaging in too many chemical dramas. It dilutes the more reactive gases and provides a steady, peaceful foundation for our planet's breath. Interestingly, Saturn's moon Titan also boasts a nitrogen-rich atmosphere, hinting at intriguing parallels even in vastly different cosmic neighborhoods. Then there is oxygen, the life-giving gas, which constitutes about 1/5 of Earth's atmosphere. Oxygen is a highly reactive element, eager to combine with others. Its presence in significant quantities is a profound indicator of active biological processes. On Earth, the vast majority of our atmospheric oxygen is a direct result of billions of years of photosynthesis by plants and microorganisms, a testament to life's quiet, persistent shaping of its environment. To find abundant free oxygen in another atmosphere would be a monumental discovery, a potential whisper of distant biology. Outside of Earth, free oxygen is exceedingly rare in planetary atmospheres, often quickly binding with other elements, making our world truly unique in this particular harmony. Carbon dioxide also plays a critical, yet varied, role in many atmospheric compositions. On Earth, it is a trace gas, a small but vital component that helps regulate our planet's temperature through the greenhouse effect. However, on worlds like Venus, carbon dioxide utterly dominates the atmosphere, forming an incredibly dense, crushing blanket that traps heat and creates a scorching, infernal surface. On Mars, conversely, carbon dioxide is also the primary component, but the atmosphere is so thin that it struggles to retain heat, leading to a frigid, desolate landscape. The sheer quantity and distribution of this one molecule can dramatically shift a planet's entire character, from icy to fiery, a quiet conductor setting the tone for a world's climate. For the giant planets, Jupiter, Saturn, Uranus and Neptune, their atmospheres are composed almost entirely of the primordial gases, hydrogen and helium. These are the lightest and most abundant elements in the universe, the original cosmic ingredients from which stars and planets formed. These gas giants are immense, deep oceans of these two elements, a powerful reminder of how they quietly gathered the very essence of the early solar nebula, holding on to them with their colossal gravitational might. Beyond these major players, every atmosphere contains a collection of trace gases and noble elements, each adding its own subtle note to the cosmic symphony. Even in minuscule amounts, these gases can have profound effects. Water vapor, for instance, is a variable trace gas in Earth's atmosphere, yet it is a powerful greenhouse gas and the driving force behind our planet's weather and climate, orchestrating cloud formations and gentle rain. On other worlds, gases like methane on Titan or sulfur dioxide on Jupiter's moon, Io, though not always dominant, reveal much about a world's hidden chemistry and geological activity. Then there are the noble gases, argon, neon, krypton and xenon. These elements are famously unreactive, quiet witnesses to cosmic history. They don't easily combine with other elements, making them like ancient time capsules within an atmosphere. For instance, the ratio of different isotopes of argon in an atmosphere can tell scientists about the amount of outgassing that occurred over geological time, a gentle echo of a planet's fiery birth. They are the background hum, the steady, unchanging element in the ever-shifting atmospheric composition. The precise blend of these gases directly dictates a world's most fundamental properties. Imagine an artist carefully selecting colors for a painting. Each pigment, each gas, contributes to the final masterpiece. The composition determines how much sunlight a planet absorbs or reflects, influencing its overall temperature. It dictates whether liquid water can exist on the surface, a crucial factor for habitability. It even affects the very color of a planet when viewed from afar. Think of the serene blue of Earth, the hazy orange of Titan, or the vibrant stripes of Jupiter. Each is a visual manifestation of its atmospheric recipe. Furthermore, how sunlight interacts with these different gas types is a key part of the invisible symphony. Some gases, like nitrogen and oxygen, gently scatter shorter wavelengths of sunlight, creating our familiar blue sky. Other gases, like carbon dioxide and water vapor, are powerful absorbers of infrared radiation, the heat radiating from a planet's surface. This absorption is what gives rise to the greenhouse effect, a natural and essential process that keeps many worlds warm enough for life. Each gas has its own particular absorption, fingerprint, a specific set of wavelengths of light it can absorb or emit. This allows us to use sophisticated telescopes and instruments to remotely analyze the light passing through or reflecting off an exoplanet's atmosphere, peacefully deciphering its hidden composition from light years away. It is like listening to a distant melody and identifying each instrument by its unique tone. So, the composition of an atmosphere is far more than just a list of elements. It is a profound expression of a world's physical laws, its chemical processes, and its grand, silent story. Each molecule, from the most abundant to the most fleeting, plays its part in this invisible symphony, harmonizing to create the unique character of every planet and moon in the gentle embrace of the cosmos. This understanding of atmospheric ingredients allows us to begin to truly comprehend the diverse, wondrous nature of worlds beyond our own. Let's gently shift our cosmic perspective to layers of serenity, from ground to space. From the quiet symphony of an atmosphere's composition, we now turn our gaze upwards, embarking on a gentle journey through the vertical structure of these magnificent gaseous envelopes. Imagine slowly drifting upwards from the surface of a world, like a feather carried by a soft breeze. As you ascend, you would pass through distinct layers of serenity, each possessing its own unique characteristics, subtly blending into one another as they reach towards the silent embrace of space. For our homeworld, Earth, this ethereal ascent begins in the layer we call the troposphere. This is the lowest and densest part of our atmosphere, where we live and breathe, and where nearly all of Earth's familiar weather softly drifts into being. Picture the clouds, the gentle rains, the soft breezes. All these phenomena unfold within the troposphere, which extends from the ground up to about 8 to 15 kilometers, depending on where you are on the planet. Its name, tropos, means turning or mixing, perfectly describing the constant churning and circulation of air within this active zone. As you ascend through the troposphere, the temperature generally decreases, becoming colder with increasing altitude, a comfortable cooling as you rise. Above the troposphere lies the stratosphere, a remarkably calm and stable layer, extending upwards to around 50 kilometers. Unlike the churning troposphere below, the stratosphere is characterized by very little vertical mixing, making it a peaceful, quiet realm. Within this serene layer lies the crucial ozone layer, a delicate shield of ozone molecules that quietly absorb most of the sun's harmful ultraviolet radiation. This absorption warms the stratosphere, causing the temperature to actually increase with altitude, a gentle inversion of the pattern seen below. Imagine a silent, invisible barrier, protecting life below from energetic solar rays, turning that harmful energy into a gentle warmth for the stratosphere itself. It is a testament to the elegant, self-regulating systems within our planet's atmosphere. Continuing our ethereal ascent, we next encounter the mesosphere. This layer stretches from about 50 to 85 kilometers above the surface. Here, the air becomes incredibly thin, and temperatures once again begin to fall with increasing altitude, reaching some of the coldest temperatures in Earth's atmosphere, sometimes dropping below -90 degrees Celsius. It's in the mesosphere that most meteors, those small cosmic travelers, peacefully burn up as they encounter enough atmospheric resistance to ignite, creating the fleeting, silent streaks of light we call shooting stars. This layer serves as another quiet protector, vaporizing incoming space debris long before it can reach the ground. Beyond the mesosphere lies the thermosphere, a layer that truly lives up to its name, thermo, meaning heat. Extending from roughly 85 kilometers up to as much as 600 kilometers, the thermosphere is where direct solar radiation causes temperatures to soar, sometimes reaching over 1,000 degrees Celsius. However, despite these seemingly extreme temperatures, the air in the thermosphere is incredibly tenuous, meaning the individual molecules are very far apart. So, while a thermometer might register a high temperature, there are so few molecules to transfer that heat that a human exposed to it would actually feel intensely cold. This is the peaceful, almost empty realm where satellites, including the International Space Station, gracefully orbit Earth, experiencing the barest whisper of an atmosphere. It is also the wondrous canvas for the auroras, the gentle, flowing curtains of light known as the northern and southern lights, created by charged particles from the sun interacting with the sparse gases in this high layer. Finally, at the outermost edge, we encounter the exosphere. This is the very boundary where Earth's atmosphere quietly fades into the vacuum of space. Starting at around 600 kilometers and extending for thousands of kilometers, the exosphere is an extremely thin, tenuous region where gas molecules are so widely spaced that collisions between them are exceedingly rare. Here, molecules simply follow ballistic trajectories, like tiny cosmic projectiles, some eventually falling back towards Earth, while others, if they achieve sufficient speed, gently escape our planet's gravitational pull altogether, drifting silently into interplanetary space. It is a slow, continuous exhalation of our world into the void, a final, soft transition from the embrace of air to the boundless quiet of the cosmos. This layered structure, though most clearly defined for Earth, is a common theme in the atmospheres of many other planets. though the specific altitudes, temperatures, and compositions of each layer vary dramatically. For instance, Venus also has a troposphere, where its weather occurs, but it is vastly thicker and hotter than Earth's. Jupiter's atmosphere also shows layers, not necessarily based on temperature inversions in the same way as Earth, but on the condensation of different chemical compounds, forming distinct cloud decks of ammonia, ammonium hydrosulfide, and water as one descends deeper. Even on moons like Titan, we find a complex, layered atmosphere with a troposphere, stratosphere, and thermosphere, each exhibiting unique thermal profiles and chemical compositions, draped in a beautiful orange haze. The general principle remains: atmospheres are not homogeneous blobs of gas, but rather intricate, stacked envelopes, each layer playing a specific role in the grand atmospheric drama. Understanding these layers allows us to appreciate the subtle elegance of planetary physics. Each boundary, each shift in temperature or composition is a testament to the complex interplay of solar radiation, gravity, atmospheric composition, and internal planetary dynamics. It is a journey from the familiar air at our feet to the unimaginable emptiness above, a peaceful ascent that reveals the quiet intricacies of our cosmic neighborhood. As we gently explore these layers, we gain a deeper appreciation for the structured beauty and profound serenity of the atmospheres that embrace worlds far and wide. Let's gently shift our cosmic perspective to the silent weight, pressure, and density in space. Having explored the layered serenity of atmospheres, let us now delve into another fundamental characteristic, the silent weight of the air itself. Imagine the invisible column of gas directly above you, reaching all the way to the edge of space. That column of air, composed of countless tiny molecules, has a subtle yet pervasive weight, pressing down gently on every surface of a world. This quiet force is what we call atmospheric pressure, and understanding it is key to deciphering how much breath a planet truly holds. Atmospheric pressure is fundamentally dictated by gravity and the total mass of the atmospheric gases. Picture all the gas molecules in an atmosphere as an immense, fluffy, cosmic blanket draped over a planet. Gravity, that persistent, invisible hand, pulls every single one of those molecules downwards. The combined force of all those downward-pulling molecules, distributed over a given area, creates the pressure we feel. So, in essence, atmospheric pressure is simply the weight of the air above us. This relationship between gravity, pressure, and density is a beautiful, self-regulating dance. On a world with stronger gravity, like Jupiter, its enormous mass means it can hold on to a far greater quantity of gas, creating immensely high pressures deep within its atmosphere. Conversely, on a smaller world with weaker gravity, like Mars, its thinner atmosphere results in significantly lower surface pressures. The density of the atmosphere, how many gas molecules are packed into a given volume, also plays a crucial role. Denser atmospheres naturally exert greater pressure. It's a fundamental physical interplay that quietly shapes every planetary environment. One of the most profound characteristics of atmospheric pressure is its tendency to decrease peacefully with increasing altitude. This is not a sudden drop, but a gradual, exponential thinning of the air, like slowly descending into a deeper, calmer ocean of gas. The pillow at the very bottom is compressed by the weight of all the pillows above it. As you move up the stack, each pillow experiences less weight from above and thus feels less compressed. In an atmosphere, the air near the surface is compressed by the entire column of air above it, making it the densest and highest pressure region. As you ascend, there are fewer and fewer air molecules above you, so the pressure steadily, calmly drops. This is why mountaineers on Earth need supplemental oxygen at very high altitudes, and why flying becomes impossible for conventional aircraft beyond a certain height. There simply isn't enough air to breathe or to generate lift. For every 5.5 kilometers you rise on Earth, for example, the atmospheric pressure approximately halves. This elegant, predictable decrease is a universal feature of any substantial atmosphere, a testament to the quiet order of physics. This gradual decrease in pressure with altitude is maintained by a state known as hydrostatic equilibrium. Imagine a perfectly still pond. The water at any given depth is under pressure from the weight of the water above it. This downward force is perfectly balanced by an equal and opposite upward force, preventing the water from collapsing. In an atmosphere, a similar balance exists. The downward force of gravity pulling air molecules downwards is precisely balanced by the upward force of the pressure gradient, the tendency of gas to expand from regions of higher pressure to lower pressure. This delicate, stable equilibrium ensures that the atmosphere remains suspended around the planet, neither collapsing entirely to the surface nor completely escaping into space. It's a continuous, peaceful negotiation of forces, maintaining the atmospheric blanket in its optimal embrace. The concept of a thinner atmosphere at higher altitudes is crucial for understanding how spacecraft interact with these celestial envelopes. For instance, when we design probes to enter the atmospheres of other planets, like the Galileo probe into Jupiter or the Huygens probe onto Titan, understanding the precise density profile is paramount. These craft use the upper, thinner layers of the atmosphere to slow down gently through aerobraking, converting immense orbital speed into heat through friction with the sparse air. This allows them to settle into orbit or descend to a landing site without expending vast amounts of rocket fuel. Imagine a delicate leaf slowly spiraling downwards, using the gentle resistance of the air to guide its descent. Even for satellites orbiting Earth, the very top layers of our atmosphere, though incredibly thin, still exert a minute drag. This subtle friction, over time, can slowly cause satellites to lose altitude, eventually leading them to drift gently back into the denser layers and burn up, completing their peaceful cosmic journey. The density of the air, even at these extreme altitudes, dictates the lifespan and trajectory of these orbiting sentinels. So, the silent weight of an atmosphere, manifested as pressure and density, is a profound and elegant aspect of planetary physics. It is the fundamental force that keeps the air wrapped around a world, thinning gradually as one ascends towards the quietude of space. This continuous, balanced interplay of gravity and gas molecules determines how much breadth a world possesses, shaping everything from its weather to the design of our exploratory spacecraft. It is a quiet, omnipresent force, ensuring that each world's atmospheric embrace is perfectly calibrated for its unique place in the cosmos. Let's gently shift our cosmic perspective to the dance of warmth, temperature, and energy flow. We have felt the silent weight of atmospheres pressing gently upon a world, and we have journeyed through their serene, layered structures. Now, let us turn our attention to the exquisite dance of warmth, the continuous flow of energy that breathes life into these gaseous envelopes. Temperature within an atmosphere is a delicate balance, shaped by the sun's distant embrace and the intimate interactions of countless molecules. We will trace how warmth flows and changes through these layers, a quiet, continuous transfer of heat that subtly sculpts every planetary environment, dictating its climate and its very character. At the heart of this dance of warmth is solar radiation, the sun's radiant energy acting as the primary heat source for most planetary atmospheres. Imagine the gentle, unwavering stream of sunlight, traveling millions of miles through the vacuum of space, only to softly encounter a planet's gaseous veil. This incoming energy, primarily in the form of visible light and some ultraviolet and infrared radiation, is the initial spark that sets the atmospheric thermal ballet in motion. However, not all of this solar energy is immediately absorbed by the atmosphere itself. Much of it, particularly the visible light, passes serenely through the atmospheric gases, reaching the planet's surface. It is the surface, whether it be solid rock, liquid oceans, or dense ice, that typically absorbs the bulk of this incoming sunlight. Picture a sun-drenched landscape gently warming under the celestial rays. Once absorbed by the surface, this energy is then re-emitted, but at a different wavelength. The surface, now warm, radiates heat back upwards in the form of infrared radiation, a form of thermal energy we perceive as warmth. This infrared radiation then becomes the crucial player in warming the lower atmosphere. Certain atmospheric gases, known as greenhouse gases, are particularly adept at absorbing and re-emitting this outgoing infrared radiation. They act like a soft, insulating blanket, trapping some of this heat and keeping the lower atmosphere and surface comfortably warm. This absorption and emission of thermal energy is a continuous, peaceful exchange, keeping the planet from radiating all its heat directly back into the coldness of space. But the flow of warmth isn't solely about absorption and emission. Atmospheric movements themselves contribute to temperature changes through a fascinating process called adiabatic cooling and warming. Imagine a parcel of air gently rising through the atmosphere. As it rises, the atmospheric pressure around it decreases, allowing the air parcel to expand. When a gas expands, its molecules have more space to move, and they do work against their surroundings. This work requires energy, which comes from the internal kinetic energy of the molecules themselves, causing the gas to cool. This is adiabatic cooling, a quiet internal process that leads to the familiar decrease in temperature as you ascend through the lower atmosphere. Conversely, if a parcel of air gently sinks, the surrounding pressure increases, compressing the air parcel. This compression adds energy to the gas molecules, causing the parcel to warm up. This is adiabatic warming. These continuous, gentle expansions and compressions of moving air parcels are fundamental to understanding the vertical temperature gradients within an atmosphere, shaping everything from cloud formation to global circulation patterns. It's a continuous, flowing process, like the quiet ebb and flow of a tide, silently modulating the temperature of the air. These processes of solar absorption, infrared re-emission, and adiabatic changes combine to create distinct vertical temperature gradients in different atmospheric layers, which we briefly touched upon earlier. On Earth, for instance, we see a general decrease in temperature with altitude through the troposphere due to adiabatic cooling and the decreasing proximity to the warm surface. Then, in the stratosphere, the presence of the ozone layer, absorbing powerful ultraviolet radiation, causes a gentle temperature inversion, where the air actually warms with increasing height. Further up, in the mesosphere, temperatures fall again, while in the incredibly thin thermosphere, direct absorption of solar X-rays and UV radiation by the sparse gas molecules leads to a dramatic, though deceptively hot, rise in kinetic temperature. Each planetary atmosphere presents its own unique thermal profile, a distinct dance of warmth choreographed by its specific composition and distance from its star. On Venus, the incredibly dense carbon dioxide atmosphere traps so much infrared radiation that its surface is a searing inferno, with temperatures high enough to melt lead, a testament to an extreme dance of warmth. On icy worlds far from the Sun, like Uranus, the primary heat source for its atmosphere often comes from its own faint internal heat, a quiet glow from within, rather than external solar radiation. The continuous flow and transformation of energy within an atmosphere is a subtle, intricate process, constantly seeking a state of balance. It dictates the existence of liquid water, the formation of clouds, the movement of winds, and ultimately, the habitability of a world. By tracing this quiet, continuous transfer of heat, we gain a deeper appreciation for the elegant physics that sculpts every planetary environment, shaping each world's character in its own unique, gentle dance of warmth. This constant flow of energy, from star to planet and through its atmosphere, is a fundamental, peaceful rhythm of the cosmos. Our journey through space now brings us to Earth's breath, our unique atmospheric harmony. After tracing the universal principles of atmospheric physics, from the quiet weight of air to the delicate dance of warmth, we now gently drift back to our own homeworld. Earth's atmosphere is a truly unique and delicate harmony, a testament to cosmic serendipity and the profound interplay of geological and biological forces. It is a breathing, living system, a perfect blend that provides the stable, peaceful conditions for life to flourish, a truly wondrous cosmic exception in the vastness of space. Imagine, for a moment, the sheer unlikelihood of such a perfect convergence of elements and processes, forming a tranquil haven amidst the cosmic extremes. It is a masterpiece of natural engineering, meticulously crafted over eons. At the heart of Earth's atmospheric harmony lies its dominant composition, approximately 78% nitrogen and 21% oxygen. This precise balance is a remarkable feature. Nitrogen, as we discussed, is a relatively inert gas, meaning it does not readily react with other elements under normal atmospheric conditions. It provides the bulk of the atmospheric pressure, offering a steady, reliable presence and acting as a gentle, yet powerful, diluent. This stable nitrogen quietly tempers the highly reactive oxygen, preventing uncontrolled combustion and creating a calm, breathable environment where fire does not consume everything in its path. Without this abundant nitrogen, our world would be a far more volatile and less hospitable place, perhaps a landscape scarred by endless intense fires, rendering complex life impossible. It is the silent, unassuming hero of our atmosphere, allowing other more dynamic processes to unfold peacefully. But it is the 21% oxygen that truly sets Earth apart as a shining cosmic jewel. This significant, enduring presence of free oxygen in such quantities is not a given. It is a direct and profound consequence of billions of years of life itself. Picture early Earth, perhaps over 3 billion years ago, with an atmosphere rich in gases like carbon dioxide, nitrogen and methane, much like what we might imagine on early Venus or Mars. There was little to no free oxygen. Then, quietly, the emergence of simple photosynthetic microorganisms, tiny, unassuming life forms in the ancient oceans, began to change everything. These organisms, like tiny cosmic breaths, started releasing oxygen as a waste product of their light harvesting processes. Slowly, over countless eons, this oxygen accumulated, first dissolving into the oceans and reacting with minerals, then gradually escaping into the atmosphere. This transformative period, often called the Great Oxidation Event, was not a sudden burst, but a monumental shift that unfolded with serene persistence, gradually altering the very chemistry of our planet's air. It eventually paved the way for the complex, oxygen-breathing life forms we see today, including ourselves. Earth's atmospheric oxygen is a living legacy, a profound, intimate connection between the air we breathe and the ancient, quiet biology that shaped our world into a nurturing cradle for life. It is the signature of life itself, etched into the sky. Beyond nitrogen and oxygen, the vital role of the water cycle intricately links our atmosphere to our vast oceans. Water vapor, though a variable trace gas, present from less than 1% to perhaps 4% of the atmosphere, is arguably the most dynamic and influential component of Earth's atmosphere. Picture the sun's gentle warmth, a soft touch on the vast expanses of our oceans, steadily evaporating water, transforming it into invisible vapor that rises gracefully into the sky. This vapor then ascends, cools, and condenses into soft, ethereal clouds, like wisps of cosmic cotton drifting across the blue. Eventually, this moisture gathers and falls back as life-giving rain or soft, silent snow, completing a continuous, serene cycle. This journey from ocean to sky and back again is a fundamental engine of Earth's climate and ecosystems. It not only replenishes our freshwater sources, but also transports immense amounts of heat from warmer equatorial regions to cooler poles, gently redistributing energy across the planet. This endless flow of water sculpts landscapes with patient, quiet force, carving valleys and nourishing ecosystems, creating a constantly refreshing and life-sustaining system that pulses with a gentle, rhythmic energy. The pervasive presence of liquid water, both on the surface and cycling gracefully through the atmosphere, is an unmistakable hallmark of Earth's unique habitability, a feature almost entirely absent on other known worlds. Another critical component of Earth's unique harmony is the ozone layer, silently residing within the stratosphere, approximately 15 to 35 kilometers above the surface. This delicate shield of ozone molecules, each composed of 3 oxygen atoms, performs an indispensable service. It absorbs the majority of the sun's most energetic and harmful ultraviolet, or UV, radiation. When a high-energy UV photon from the sun encounters an ozone molecule, it breaks one of its chemical bonds, absorbing the harmful energy in the process. This gentle, continuous absorption shields all life below from cellular damage, genetic mutations, and disease. Without this protective blanket, this quiet sentinel, the intense UV radiation would sterilize Earth's surface, making it impossible for complex life to thrive on land or near the surface of the oceans. The ozone layer tirelessly guards against a destructive cosmic threat, a silent, powerful guardian, allowing the peaceful evolution of intricate biological systems beneath its invisible protection. It is another profound example of the extraordinary, interconnected balance that makes Earth so special and so conducive to a thriving biosphere. The very atmosphere of Earth, therefore, is not merely a static collection of gases. It is a profound testament to the co-evolution of a planet and its life. The initial geology of early Earth provided the outgassed components, forming a primordial atmosphere, but it was the quiet, persistent work of billions of years of biological processes, from ancient cyanobacteria to lush forests, that continuously refined and transformed it into the breathable, protective atmosphere we cherish today. This intimate, reciprocal relationship means that Earth's atmosphere is, in a very real sense, a living, breathing component of a grand, interconnected system, constantly interacting with its oceans, land, and all forms of life. It's a dynamic, planetary-scale metabolism, perpetually exchanging and recycling its precious resources. This unique atmospheric harmony ensures remarkable stability, a quiet resilience that has endured through eons. The consistent blend of gases, the regulating water cycle that moderates temperatures, and the protective ozone layer that filters harmful radiation all work together to create conditions that buffer against extreme temperature swings and energetic cosmic threats. Imagine a perfectly tuned instrument, not just a single melody, but a complex orchestral piece where each section, each string and wind plays its part in a harmonious, balanced symphony. This profound stability has allowed life to diversify into countless forms, to evolve into intricate ecosystems, and to spread across our world from the deepest oceans to the highest mountains, finding a niche in almost every corner of this gentle blue sphere. When we observe distant exoplanets, searching for subtle signs of life, it is precisely this kind of unique atmospheric signature, the simultaneous presence of abundant oxygen, significant water vapor, and perhaps a small amount of methane, that would be a compelling indicator. These combinations of gases are generally considered to be out of chemical equilibrium. They would naturally react and disappear quickly unless constantly replenished by an active source, like biology. Such a finding would strongly suggest the presence of active, thriving life, silently transforming its world, just as it did on early Earth. So, as we contemplate Earth's breath, our unique atmospheric harmony, we are reminded of the profound interconnectedness of all things on our home world. It is a system of extraordinary balance, quiet resilience, and profound beauty, a cosmic exception that allows us to exist, to breathe, and to marvel at the wonders of the universe. This peaceful reflection on our own atmosphere provides a comforting anchor, a grounding in the familiar, as we prepare to venture back out into the diverse and sometimes extreme atmospheric landscapes of other worlds, appreciating the quiet marvel of the air that cradles our existence. Let's gently shift our cosmic perspective to the sun's gentle touch, solar radiation, and atmospheric response. Having explored Earth's unique atmospheric harmony, let us now broaden our view to a more universal interaction, the sun's gentle touch on every world. The radiant light from our star, indeed from any star, bathes all celestial bodies in its warmth and energy. Yet each atmosphere responds differently to this luminous embrace, creating a captivating interplay of light and gas that shapes both the visual and energetic fabric of a planet. It's a quiet cosmic ballet, painting our skies with tranquil colors and delivering the vital energy that drives all atmospheric processes. To truly appreciate this interaction, we must first understand the nature of solar radiation itself. Sunlight is not merely a single, uniform glow. It is a rich tapestry of energy, a broad spectrum of electromagnetic waves. Imagine a peaceful rainbow, stretching far beyond the colors our eyes can perceive. This electromagnetic spectrum includes not only the familiar visible light that paints our world, but also invisible components like powerful ultraviolet radiation, which can be damaging, infrared radiation, which carries warmth, and even radio waves, microwaves, and X-rays. Each of these different wavelengths carries distinct amounts of energy, and each interacts uniquely with the various gases and particles within an atmosphere. One of the most beautiful and familiar ways an atmosphere responds to sunlight is through scattering, a gentle redirection of light that creates the tranquil colors of our skies. There are two primary forms of this scattering. The first is called Rayleigh scattering, which explains why Earth's sky is such a serene blue during the day. Imagine tiny air molecules, primarily nitrogen and oxygen, as minuscule obstacles for the incoming sunlight. These tiny particles are particularly effective at scattering shorter, bluer wavelengths of light much more efficiently than longer, redder wavelengths. As sunlight enters our atmosphere, the blue light is gently dispersed in all directions, creating the soft azure canopy above us. At sunrise and sunset, when the sun's rays travel through a much thicker slice of atmosphere, more of the blue light is scattered away, allowing the reds and oranges to pass through more directly, painting the horizon with warm, calming hues. It's a natural, artistic masterpiece unfolding daily. The second type of scattering is me scattering, which primarily occurs when light interacts with larger particles, such as the water droplets or ice crystals that form clouds, or the fine dust particles suspended in the air. Unlike Rayleigh scattering, me scattering is not strongly dependent on the wavelength of light. This means it scatters all colors of light almost equally. This is why clouds typically appear white or grey. They are simply scattering all colors of sunlight back to our eyes in roughly equal proportions. Imagine a soft, luminous veil, gently redirecting the sun's full spectrum. If these cloud droplets become very dense or thick, less light can pass through or be scattered back, making the clouds appear darker and more foreboding, yet still a part of this natural visual process. Beyond scattering, an atmosphere also responds to solar radiation through absorption, a process where gases gently capture specific wavelengths of light. This absorption is crucial for the energy balance of a planet and for protecting its surface. For instance, in Earth's atmosphere, the ozone layer, as we discussed, powerfully absorbs harmful ultraviolet radiation. Picture these ozone molecules quietly intercepting the energetic UV photons, transforming their destructive potential into a gentle warmth for the stratosphere itself. This absorption shields life on the surface, allowing for its peaceful continuation. Similarly, certain gases, known as greenhouse gases like water vapor and carbon dioxide, are particularly adept at absorbing infrared radiation. While they allow most visible sunlight to pass through to warm the surface, they then gently capture the infrared heat radiated back from the warmed ground. This process prevents too much heat from escaping directly into space, keeping the planet comfortably warm. This selective absorption of different wavelengths by various gases creates a complex and vital thermal blanket, a quiet regulator of a world's temperature. The balance between how much solar radiation an atmosphere and its planet absorb versus how much they reflect back into space is known as planetary albedo. Imagine a world peacefully floating in space. Its albedo is a measure of its overall reflectivity, expressed as a fraction or percentage. A perfectly black body would absorb all incoming sunlight and have an albedo of 0, while a perfectly white body would reflect all light and have an albedo of 1. Different surfaces and atmospheric components contribute to a planet's albedo. Bright white clouds or polar ice caps, for example, have a high albedo, reflecting a significant portion of sunlight directly back into space, thereby exerting a cooling effect. Darker surfaces, like oceans or forests, have a low albedo, absorbing more solar energy and contributing to warming. Dust particles in the atmosphere can also affect albedo, either reflecting light back into space or absorbing it, depending on their composition and height. The overall planetary albedo is a crucial factor in determining a world's average temperature and energy balance. It's a quiet, global negotiation of incoming and outgoing light, maintaining a delicate thermal equilibrium. This quiet interplay of light and gas, scattering, absorption, and reflection shapes the very visual and energetic fabric of a planet. It determines not only the color of its sky and clouds, but also how much energy it retains to drive its atmospheric circulation, its weather systems, and its overall climate. From the serene blue of our own world to the hazy orange glow of Titan, or the vibrant banded colors of Jupiter, each celestial canvas is painted by the sun's gentle touch and the unique response of its atmosphere. Why? Understanding these subtle yet powerful interactions allows us to appreciate the intricate beauty and profound physics behind the celestial tapestries that adorn worlds across the silent, vast universe. Continuing our peaceful voyage through the universe, the warming blanket, Earth's natural greenhouse effect, having appreciated the sun's gentle touch, and the beautiful ways light interacts with different atmospheres, let us now focus on a natural phenomenon that is absolutely essential for life on our home planet, the greenhouse effect. Far from being a source of alarm in its natural state, this vital process acts like a comforting, invisible warming blanket, gently wrapping Earth and creating the cozy, habitable climate we all cherish. We will explore how this natural atmospheric warmth keeps our world from becoming an icy, lifeless sphere, revealing a fundamental and peaceful aspect of planetary habitability. The essence of the greenhouse effect lies in the unique properties of certain atmospheric gases, aptly named greenhouse gases. These are not the most abundant gases in our atmosphere. Indeed, they make up only a small fraction of the total air. Yet, their molecular structure allows them to perform a crucial, life-sustaining function. The primary natural greenhouse gases on Earth include water vapor, carbon dioxide, and methane. While nitrogen and oxygen, our atmosphere's dominant components, interact very little with thermal radiation, these trace gases are highly effective at it. The mechanism of the greenhouse effect is a beautiful, subtle interplay of energy. Imagine sunlight, primarily in the form of visible light, gently streaming through Earth's atmosphere. Most of this visible light passes right through our air and reaches the planet's surface, our land, oceans, and ice. The surface then absorbs this solar energy, warming up, much like a dark stone warming in the sun. As the Earth's surface warms, it begins to radiate this absorbed energy back upwards, not as visible light, but as longer wavelength infrared radiation, the kind of thermal energy we feel as warmth. Now, this is where our special greenhouse gases come into play. Instead of allowing all of this infrared radiation to simply escape directly back into the coldness of space, these molecules quietly absorb a significant portion of it. Picture a carbon dioxide molecule gently intercepting an infrared photon. This absorption causes the molecule to vibrate, gaining a tiny bit of energy, but these molecules do not hold on to this energy indefinitely. Instead, they quickly re-emit the infrared radiation, sending it out in all directions, some upwards towards space, but critically, also some downwards, back towards the Earth's surface and the lower atmosphere. It is this re-emission of heat back towards the planet that creates the warming effect, much like how a physical blanket traps the heat radiating from your body. This continuous cycle of absorption and re-emission effectively slows down the escape of heat from Earth, maintaining a much higher average surface temperature than our planet would otherwise possess. The essential role of this natural greenhouse effect in maintaining Earth's habitable temperature cannot be overstated. Without these vital greenhouse gases, our planet would be a frozen, desolate world, with an average surface temperature plummeting to a frigid -18 degrees Celsius or 0 degrees Fahrenheit. But such extreme cold liquid water would be impossible to sustain across the globe, locking up all moisture in ice. Life, as we know it, would likely never have emerged, or at least would be confined to extremely limited deep ocean environments around hydrothermal vents. The natural greenhouse effect provides the cozy, life-sustaining warmth that elevates Earth's average temperature to a comfortable 15 degrees Celsius or 59 degrees Fahrenheit, allowing our vast oceans to remain liquid and supporting the incredible diversity of life we see today. It is a fundamental, peaceful aspect of planetary habitability, a cosmic blessing that we often take for granted. It is important to appreciate the crucial distinction between this natural greenhouse effect and what is often referred to as the enhanced greenhouse effect. The natural greenhouse effect, as we have explored, is a perfectly balanced and utterly essential planetary process, a gift of our atmosphere that allows life to thrive. It has been a stable, quietly functioning system for billions of years, carefully regulated by geological and biological processes, ensuring a consistent, life-friendly temperature. The enhanced greenhouse effect, in contrast, refers to the additional warming that occurs when human activities, such as the burning of fossil fuels and deforestation, release extra greenhouse gases into the atmosphere beyond the natural balance. These additional gases, primarily carbon dioxide and methane, augment the natural warming blanket, making it thicker and more insulating. Imagine adding too many layers to your comforting blanket. It can quickly become uncomfortably warm. This subtle but significant alteration to Earth's delicate energy balance is what leads to changes in our planet's climate. This distinction is vital for a clear, calm understanding of the physics involved. For example, Venus, our planetary neighbor, offers a stark yet peaceful example of a runaway greenhouse effect, which we will explore in more detail later. Its incredibly dense atmosphere, overwhelmingly composed of carbon dioxide, traps an immense amount of heat, creating surface temperatures hot enough to melt lead. While Earth's natural greenhouse effect is a gentle, life-giving warmth, Venus demonstrates what happens when that warming blanket becomes overwhelmingly thick, transforming a world into an inferno. So, the natural greenhouse effect is a cornerstone of Earth's habitability, a beautiful and essential physical process that sustains our world. It is a testament to the elegant self-regulation of our planet, a quiet, continuous interaction between sunlight, surface, and specific atmospheric gases that ensures a stable, temperate climate. This invisible warming blanket is a profound gift, a fundamental and peaceful aspect of Earth's unique place in the cosmos, allowing the vibrant tapestry of life to flourish under its comforting embrace. Continuing our peaceful voyage through the universe, Venus's fiery veil, the runaway greenhouse. From Earth's gentle warmth, sustained by a balanced natural greenhouse effect, we now gently drift to its stark, fascinating counterpoint, Venus. Often called Earth's twin due to its similar size and mass, Venus presents an atmosphere utterly transformed by an intense runaway greenhouse effect. Its thick, swirling carbon dioxide atmosphere creates an inferno on its surface, a powerful yet distant and quiet reminder of how a planet's delicate climate balance can shift dramatically, altering its fate forever. We explore this dense, scorching environment, a testament to the powerful, quiet forces shaping planetary destinies, a profound example of cosmic evolution. The most striking feature of Venus's atmosphere is its dominant composition, a thick, pervasive veil of carbon dioxide. Imagine an atmosphere that is over 96% carbon dioxide, with only traces of nitrogen and other minor gases. This is in stark contrast to Earth's atmosphere, which, as we know, contains only a tiny fraction of a percent of carbon dioxide, balanced by its vast oceans and thriving biosphere. On Venus, this overwhelming abundance of carbon dioxide creates an atmospheric pressure at the surface that is truly crushing, more than 90 times that of Earth's sea level pressure. To visualize this, consider being almost a kilometer deep in Earth's oceans, where the weight of the water above exerts an immense silent force. This is the constant, unyielding pressure felt on the Venusian surface, a silent, immense weight pressing down from all directions, capable of crushing unreinforced spacecraft. Beneath this immense, CO2-rich blanket lies a landscape of unimaginable heat. The surface temperatures on Venus average a staggering 462 degrees Celsius or 864 degrees Fahrenheit. This is hotter than the melting point of lead, hotter than the inside of a self-cleaning oven, and remarkably, even hotter than Mercury, which is much closer to the Sun. Imagine a world perpetually shrouded in a dry, superheated oven where no liquid water could possibly exist. Any water molecule reaching the surface would instantly flash into vapor, unable to pool or flow. It is a world of extreme, constant, and profound heat, a surface that glows faintly red in the infrared, a truly alien and fiery realm. Adding to Venus's enigmatic nature are its persistent, bright clouds, which completely obscure the surface from view in visible light. These aren't the soft white water clouds we know on Earth. Instead, they are primarily composed of droplets of sulfuric acid mixed with sulfur dioxide gas. Picture vast, yellowish-white hazes stretching for tens of kilometers, beginning high in the atmosphere, about 45 to 70 kilometers above the surface. These clouds are remarkably reflective, bouncing about 70% of the incoming sunlight back into space, giving Venus its dazzling brightness when viewed from Earth. These sulfuric acid clouds are formed through complex chemical reactions involving sulfur and water vapor, high in the Venusian atmosphere. While they reflect sunlight, they also contribute to trapping some of the thermal energy, adding yet another insulating layer to the planet's intense warming. This constant, gentle production and circulation of sulfuric acid droplets creates a strangely beautiful, yet utterly inhospitable sky, where drops of acid rain fall but evaporate long before ever reaching the superheated ground. The origin of Venus's present-day inferno lies in the runaway greenhouse effect, a powerful and irreversible mechanism that fundamentally transformed the planet. Scientific models and observations suggest that early Venus might have been much more like early Earth, potentially possessing vast oceans of liquid water and a more moderate climate. However, being closer to the Sun, Venus naturally received more solar radiation than Earth. Over astronomical timescales, as the Sun naturally grew brighter and its output slowly increased, Venus's surface temperatures would have gradually, subtly increased. This initial, slight warming would have caused more and more water to evaporate from its nascent oceans, increasing the amount of water vapor in its atmosphere. Water vapor, as we know, is a potent greenhouse gas, exceptionally effective at trapping heat. So, more water vapor in the atmosphere meant even more heat was trapped, leading to further warming of the surface. This created a relentless positive feedback loop, a quiet, self-reinforcing cycle. Warmer temperatures led to more evaporation, which led to more water vapor, which in turn led to even warmer temperatures. Imagine this cycle quietly, yet relentlessly, accelerating, spiraling out of control. As temperatures continued to climb, the oceans would have eventually boiled away entirely, turning into a superheated, dense steam atmosphere. This dense water vapor would have risen higher into the atmosphere, where it could then be broken apart by the sun's powerful ultraviolet radiation into its constituent hydrogen and oxygen atoms. The light hydrogen atoms, being so small and energetic, would have then slowly but surely escaped into space, drifting away into the cosmic void. This process permanently stripped Venus of its water, leaving the oxygen behind to react with surface rocks or other elements, preventing it from recombining into water. Simultaneously, with the planet becoming hotter and drier, carbon dioxide, which had been locked away in Venus's rocks and surface minerals, much like it is on Earth in vast limestone deposits, would have begun to outgas from intense volcanic activity and chemical reactions triggered by the heat. This liberated carbon dioxide accumulated massively in the atmosphere, with no oceans to dissolve and sequester this carbon dioxide, and crucially, no biological processes like photosynthesis to convert it into organic matter or back into rocks. The CO2 accumulated relentlessly. This transformed the initial warming blanket into a suffocating, super-insulating shroud, thickening to 90 times Earth's atmospheric mass. This massive buildup of carbon dioxide, combined with the irreversible loss of water, irrevocably led to the runaway greenhouse effect that defines Venus today. It was a slow, geological catastrophe, unfolding over hundreds of millions of years, an irreversible tipping point crossed in the planet's atmospheric evolution, sealing its fiery fate. Studying Venus gives us a profound, albeit distant, understanding of the immense potential power of a greenhouse effect unconstrained. It is a natural laboratory, demonstrating the dramatic, fundamental shift a planet can undergo if its delicate energy balance is severely disrupted. While Earth's natural greenhouse effect is a benevolent warmth, cradling life, Venus stands as a silent testament to the extreme forces that can quietly shape a world's fate, turning a potentially habitable planet into a scorching pressure cooker inferno. It serves as a calm, scientific example of the profound impact atmospheric composition can have on a planetary environment, an extreme lesson whispered across the vastness of space, reminding us of the delicate balances at play in our cosmic neighborhood. As we float further into this vast topic, Mars is whispering past, a thin, evolving atmosphere. From the fiery veil of Venus, a world suffocated by a runaway greenhouse, we now gently shift our gaze to Mars, the red planet. Mars holds a thin, whispering atmosphere of carbon dioxide, a stark and poignant contrast to its much wetter, warmer past. We will explore the delicate remnants of this once thicker air, its connection to the serene polar caps, and the vast, silent dust storms that occasionally sweep across its desolate surface, revealing a world slowly, peacefully evolving over cosmic eons. It's a story of quiet loss and subtle, enduring change, a poignant reminder of the fragility of planetary environments. The current Martian atmosphere is incredibly thin, barely 1% the density of Earth's atmosphere at sea level. Imagine air so tenuous that if you were to stand unprotected on the Martian surface, your body fluids would instantly boil away due to the low pressure, a phenomenon known as ebulism. It is overwhelmingly composed of carbon dioxide, making up about 95% of the total gases, with small, barely detectable amounts of nitrogen, argon, and other trace elements. This thin, frigid envelope does little to trap heat, meaning its greenhouse effect is minimal. This results in extremely cold surface temperatures that average around -63 degrees Celsius or -81 degrees Fahrenheit, dipping even lower at the poles. The Martian sky, rather than being blue, often appears as a pale butterscotch color due to the ever-present fine dust particles suspended within the thin air. This thin carbon dioxide atmosphere is intricately connected to Mars's majestic polar caps. Unlike Earth's ice caps, which are primarily water ice, Mars's polar caps have a dynamic seasonal component made of frozen carbon dioxide or dry ice. Picture the quiet beauty of a Martian winter as temperatures plummet, A significant portion of the atmospheric carbon dioxide freezes directly onto the polar caps, quietly expanding their size and forming layers that can be several meters thick. When spring returns, this dry ice gently sublimates. That is, it transitions directly from solid to gas without becoming liquid, releasing vast quantities of carbon dioxide back into the atmosphere. This seasonal exchange causes the atmospheric pressure on Mars to fluctuate by as much as 20 to 30% over a single Martian year, a slow, rhythmic breathing of the planet, a silent testament to the extreme cold that defines its climate. Beneath these dynamic, seasonal dry ice layers, permanent caps of water ice also exist, holding ancient reserves of frozen water, a quiet reservoir of the planet's watery past. Yet, this thin, frigid atmosphere whispers of a far more vibrant past, one filled with liquid water and a potentially more hospitable environment. Scientific evidence, meticulously gathered by a fleet of rovers like Curiosity and Perseverance, and by orbiting spacecraft such as Mars Reconnaissance Orbiter, paints a compelling picture of an early Mars with a much thicker atmosphere and, crucially, an abundance of liquid water flowing across its surface. Picture ancient river valleys, now dry and eroded channels winding across the plains. Vast, quiet lakebeds, some hundreds of kilometers wide, where sediments patiently accumulated, and even possible ocean coastlines, all carved by the gentle, persistent flow of water billions of years ago. Minerals found by rovers, such as clays and sulfates, are direct indicators, as they only form in the presence of liquid water, providing silent geological proof of this wetter era. This early Mars likely had a much warmer climate, thanks to a more substantial carbon dioxide atmosphere that would have provided a far more effective greenhouse effect, retaining more of the sun's warmth. It was a world perhaps not unlike early Earth, harboring the serene potential for the emergence of life. But what happened to this once thicker atmosphere and its life-giving water? The primary culprit is atmospheric escape, a slow, inexorable process that relentlessly stripped Mars of its vital blanket of air over billions of years. Unlike Earth, Mars is a smaller planet, and its gravitational pull, while significant, is simply weaker. Crucially, early in its history, Mars lost its global magnetic field. On Earth, our magnetic field acts like an invisible shield, a protective bubble that deflects the relentless, charged particles of the solar wind away from our atmosphere. Without such a shield, Mars's upper atmosphere was directly exposed to this constant cosmic breeze, a torrent of energetic particles streaming from the sun. Imagine the solar wind as a gentle, yet persistent, cosmic sandblaster. Over billions of years, these energetic particles silently, relentlessly stripped away Mars's atmospheric gases, molecule by molecule. This process, known as solar wind stripping, preferentially affected lighter molecules, including water vapor. When water vapor reached the upper atmosphere, it was broken apart by powerful solar ultraviolet radiation into its constituent hydrogen and oxygen atoms. The lighter hydrogen atoms, being so small and energetic, were then easily carried away by the solar wind, permanently losing the water from the planet. This slow, quiet erosion, unfolding over cosmic timescales, gradually transformed Mars from a potentially water-rich and habitable world to the cold, dry, and thin-aired planet we know today. NASA's MAVEN mission continues to quietly study this very process, observing the subtle loss of Martian atmosphere even in the present day. Even with its thin atmosphere, Mars still experiences dramatic atmospheric phenomena, particularly vast dust storms that can be truly immense. These storms can range from localized whirlwinds, known as dust devils, which gracefully dance across the landscape, to colossal, planet-encircling events. Picture a gentle gust of wind lifting incredibly fine, reddish dust particles from the Martian surface. Once airborne, these particles, being dark, absorb sunlight, warming the surrounding atmosphere. This warming makes the air more buoyant, causing it to rise and further intensify the winds, lifting even more dust from the parched ground. This positive feedback loop can escalate rapidly, leading to global dust storms that engulf the entire planet, sometimes for months at a time. During these events, the entire Martian sky turns a hazy, opaque red-orange, obscuring the surface from view, as we saw during the Spirit and Opportunity rover missions. Despite their immense scale, these storms unfold with a quiet, majestic power, a testament to the planet's enduring atmospheric dynamics, even with so little air to work with. Mars's whispering past, and its thin, evolving atmosphere offer a poignant lesson in planetary evolution. It reminds us that a planet's climate and atmospheric state are not fixed, but are products of complex, long-term interactions between its geology, its internal dynamics, its star, and its magnetic field. The quiet transformation of Mars, from a potentially water-rich world to a cold desert, is a testament to the powerful, yet patient, forces that shape celestial bodies over cosmic eons. It fosters a sense of gentle melancholy, but also a deeper appreciation for the delicate balance that sustains life on our own blue planet. The faint breath of Mars continues its silent journey through the cosmos, a quiet chronicle of change, patiently awaiting the next chapter of human exploration. As we drift deeper into our exploration, airless wonders, Mercury and the Moon's exospheres, we have explored worlds cloaked in dense, fiery veils, and others with thin, whispering breaths. Now, let us consider worlds that offer little more than a ghost of an atmosphere, a faint and tenuous presence known as an exosphere. These are the truly airless wonders, bodies like Mercury and Earth's own moon, where the quiet interplay of the solar wind and their barren surfaces creates an incredibly thin, transient veil of scattered particles, a subtle, almost imperceptible breath in the vastness of space. So, what exactly defines an exosphere? Imagine pushing the boundaries of an atmosphere to its absolute limit, where the air becomes so incredibly thin that individual gas molecules are extremely far apart. In an exosphere, these molecules are so sparse that they are more likely to collide with the surface of the celestial body than with each other. There is virtually no internal atmospheric pressure to speak of, and the concept of distinct layers, as we discussed for Earth, no longer applies. It's a region where the atmosphere essentially blends into the vacuum of space, a faint, ethereal presence on the cusp of nothingness. For a celestial body to retain a more substantial atmosphere, it requires both sufficient gravity to hold onto the gas molecules and a mechanism to replenish those gases faster than they escape. Mercury and the Moon, being relatively small and lacking strong gravity, coupled with their exposure to intense solar radiation and the solar wind, cannot hold on to a traditional, dense atmosphere. Their tenuous exospheres are fascinating precisely because they challenge our conventional definition of air. The particles that make up these whisper-thin exospheres originate from a few quiet, constant processes. One significant source is the gentle interaction of the solar wind with the surface. Remember the solar wind, that constant stream of charged particles flowing from the sun. When these energetic particles quietly impact the unprotected surface of Mercury or the Moon, they can literally knock individual atoms off the surface rocks, a process called sputtering. These ejected atoms then briefly float above the surface, forming a temporary, incredibly thin cloud of gas before eventually falling back down or escaping into space. Another source is the slow, continuous outgassing from the interior of these bodies, though this is very minimal compared to volcanically active planets. Also, impacts from micrometeoroids, tiny specks of cosmic dust, can vaporize small amounts of surface material, contributing momentarily to the exosphere. On the Moon, for example, the exosphere contains trace amounts of sodium, potassium, and argon, all gently released from the lunar soil through these processes. Imagine these tiny, fleeting particles as silent, restless spirits, briefly liberated from the surface before drifting away or settling back down. The transient nature of these exospheres is another defining characteristic. Unlike the stable, recirculating atmospheres of Earth or Venus, the particles in an exosphere are not held in a long-term balanced system. They are constantly being created and constantly escaping. Imagine a quiet fountain where the water droplets spray upwards and then quickly fall back or evaporate. The exosphere is a dynamic yet tenuous equilibrium of input and output. A molecule might be gently sputtered off the surface, float for a short while, and then either fall back to the surface or, if it gains enough energy, drift away into the vastness of space, forever lost from that world. This constant flux means that the composition and density of an exosphere can vary subtly over time, influenced by solar activity or even the angle of the sun. Let's quietly observe Mercury, the innermost planet, as a prime example. Due to its proximity to the sun, it experiences extreme temperature swings, from scorching daytime highs of over 400 degrees Celsius to frigid nighttime lows of -170 degrees Celsius. This vast temperature difference, combined with its weak gravity, means any significant atmosphere would quickly be lost. Yet Mercury does possess a trace exosphere, detected by missions like Messenger. This includes elements like sodium, potassium, oxygen, and helium, gently released from its sun-baked surface by the solar wind. These atoms fluoresce faintly when illuminated by sunlight, making them detectable, a very subtle glow in the dark vacuum. Our own moon also hosts an exosphere. Despite appearing utterly airless to our eyes, sensitive instruments have detected minute quantities of gases, like helium, neon, and argon, originating from the solar wind itself being implanted into the lunar soil and then gently released. The Apollo missions even deployed seismometers on the moon, which could detect the impact of even tiny micrometeoroids hitting the surface, contributing to this transient gaseous veil. For lunar missions, this exosphere is negligible for spacecraft entry, but its study offers peaceful insights into the subtle interactions between planetary surfaces and the space environment. It's a reminder that even in seemingly empty places, there are always quiet, ongoing physical processes. Studying these airless wonders and their tenuous exospheres offers valuable, peaceful insights into the very edges of atmospheric science. They represent the minimalist extreme, where the distinction between atmosphere and space blurs into a subtle, almost poetic dance of individual atoms. They teach us about the subtle ways celestial bodies interact with their stellar environment, revealing how even a faint whisper of gas can tell a story about a world's composition, its gravity, and its ongoing quiet evolution under the constant, gentle touch of the solar wind. These subtle presences in the vastness are a testament to the fact that even the most seemingly barren worlds are constantly, if quietly, exchanging matter with the cosmos around them. Let's gently shift our cosmic perspective to the great planetary circulations, winds, and weather patterns. Having quietly observed the subtle exospheres of airless worlds, let us now turn our attention to planets embraced by more substantial atmospheres, where a magnificent ballet of air unfolds. Across these worlds, vast, slow currents of air create mesmerizing global circulation patterns, orchestrating the winds and weather that define each planetary landscape. We will gently trace these planetary winds, from Earth's elegant Hadley cells to the subtle spiraling influence of the Coriolis effect, understanding how energy is quietly redistributed across a spinning world, creating its unique and ever-changing weather tapestry. The primary driver of all atmospheric circulation is the uneven heating of a planet by its star. Imagine sunlight gently warming the equatorial regions of a world much more intensely than its polar regions. This creates a fundamental imbalance of energy, a quiet imperative for heat to flow from warmer areas to colder ones. In a very simple, non-rotating world with an atmosphere, warm air would rise at the equator, flow towards the poles, cool, sink, and then flow back towards the equator along the surface. This would form two large, elegant circulation cells. However, planets spin, and this rotation introduces a beautiful and profound subtlety to the atmospheric dance, the Coriolis effect. Picture yourself gently floating above a spinning planet. As air moves across the surface, the planet rotates beneath it, deflecting the moving air. In the northern hemisphere, this deflection is always to the right of the direction of motion, and in the southern hemisphere, it's to the left. This gentle, spiraling influence doesn't create the wind, but it beautifully steers and shapes its path, breaking up what would otherwise be simple, two-cell circulation into more complex, yet predictable, patterns. On Earth, this interplay of differential heating and the Coriolis effect gives rise to three distinct global circulation cells in each hemisphere: the Hadley cell, the Ferrel cell, and the polar cell. The Hadley cells are the largest and most energetic. Imagine warm, moist air gently rising at the equator, creating a zone of low pressure and frequent, light precipitation. As this air rises, it flows poleward in the upper atmosphere, gradually cooling. Around 30 degrees latitude, this now cooler, drier air gently sinks, creating zones of high pressure and typically clear skies, which is why many of Earth's deserts are found at these latitudes. This sinking air then flows back towards the equator along the surface, forming the steady, gentle trade winds which sailors have relied upon for centuries. It's a vast, continuous loop, quietly transporting warmth from the equator towards the mid-latitudes. Adjacent to the Hadley cells are the Ferrel cells, located in Earth's mid-latitudes, roughly between 30 and 60 degrees latitude. These cells are somewhat less directly driven by temperature differences. Instead, they act as a gentle buffer or gear, driven indirectly by the energy exchange between the Hadley and polar cells. Here, air tends to flow poleward at the surface, encountering warmer air from the tropics and cooler air from the poles, creating the more variable weather patterns we often experience in temperate zones. The upper air in the Ferrel cell flows equatorward, completing this complex yet stable middle layer of circulation. Finally, at the highest latitudes near the poles are the polar cells. Here, cold, dense air gently sinks at the poles, creating high-pressure zones. This frigid air then flows equatorward along the surface, towards 60 degrees latitude, forming the polar easterlies. As it meets the warmer air from the Ferrel cells, it rises, completing the circulation back to the poles in the upper atmosphere. It's a quiet, cold circulation, helping to regulate the planet's heat balance, even at its coldest extremes. These large-scale circulation patterns are not just theoretical constructs, they are the unseen architects of our planet's weather tapestry. They quietly govern where deserts form, where rainforests flourish, and where major storm systems are likely to develop. For instance, the upward motion of air in the Hadley cell's equatorial zone contributes to the moist, warm climate of tropical regions, while the sinking air at 30 degrees latitude explains the dry conditions of many of the world's great deserts. Furthermore, the boundaries between these circulation cells, particularly the Ferrel and polar cells, are where we find jet streams. These are relatively narrow bands of exceptionally strong, fast-flowing winds, typically found in the upper troposphere. Imagine vast, invisible rivers of air, quietly flowing at speeds sometimes exceeding 300 kilometers per hour. Jet streams play a crucial role in steering major weather systems and influencing temperature patterns across continents. They are the dynamic pathways along which many of our large-scale weather phenomena, from gentle rainfronts to significant storms, gracefully travel. The ultimate purpose of these great planetary circulations is the quiet, continuous transport of energy from the equator to the poles. The sun's energy is not distributed evenly. The equatorial regions receive a surplus, while the poles experience a deficit. Without atmospheric and oceanic circulation, the equator would grow progressively hotter and the poles colder, leading to extreme temperature differences. These circulation cells act as vast, natural convection systems, gently moving heat around the globe, striving for a more balanced thermal state. It's a massive, quiet effort to stabilize the planet's temperature, a testament to the elegant self-regulating systems inherent in nature. This calm, ordered dance of planetary winds and global weather patterns is not unique to Earth. Similar, though often vastly different, circulation systems exist on other worlds with substantial atmospheres. Venus, for example, with its slow rotation, exhibits a single, massive, Hadley-like cell extending from its equator to its poles. The gas giants, with their rapid rotations and deep atmospheres, display complex, multi-banded circulation patterns, like the serene, colorful stripes we observe on Jupiter. Understanding these fundamental principles of atmospheric circulation allows us to decipher the majestic, quiet ballet of air on any spinning world, revealing the intricate physics that shapes their unique atmospheric tapestry. Our journey through space now brings us to Jupiter's grand swirls, a deep hydrogen-helium ocean. We have charted the grand circulations of Earth's atmosphere, witnessing the orderly dance of winds and weather. Now, our journey takes us to a truly colossal world, a realm where atmosphere and planet become almost indistinguishable. Jupiter. The largest planet in our solar system, Jupiter is a magnificent gas giant, a world whose atmosphere is a deep, swirling ocean of hydrogen and helium. We will quietly observe its iconic Great Red Spot and its colorful, banded clouds of ammonia and methane, each a testament to the immense, calm forces at play within this magnificent celestial body. A silent, swirling masterpiece of cosmic fluid dynamics. It is a world that commands awe, not with solid ground, but with an endless expanse of dynamic, gaseous beauty. The dominant composition of Jupiter's atmosphere is overwhelmingly hydrogen and helium. Imagine an atmosphere that is nearly 90% hydrogen and about 10% helium by number of atoms, with much smaller amounts of other trace gases like methane, ammonia, and water vapor. These are the two lightest and most abundant elements in the entire universe, the primordial ingredients from which stars, and indeed our entire solar system, originally formed. Jupiter, with its truly immense gravity, was able to capture and hold on to these original nebula gases during its formation, with such power that it created an atmospheric mass far exceeding that of all the other planets combined. This deep hydrogen-helium ocean is not just a thin layer that gradually fades into space. It extends downwards for tens of thousands of kilometers, gradually transitioning from a gaseous state to a liquid metallic hydrogen interior, blurring the very line between what we traditionally define as atmosphere and what is the planet's interior. It is an unbroken continuum of fluid, from the visible cloud tops to the deep, high-pressure core, an astonishing testament to its colossal scale. One cannot speak of Jupiter without quietly contemplating its most famous feature, the Great Red Spot. This colossal, persistent storm is perhaps the most iconic atmospheric phenomenon in our solar system, a true marvel of cosmic longevity. Imagine a vast oval vortex, larger than Earth itself, calmly churning for at least 350 years, if not far longer, having been observed since the 17th century. Its reddish hue, which can vary in intensity from brick red to pale orange, is thought to be caused by complex chemical reactions involving sunlight and upwelling compounds like phosphorus, sulfur, or even organic molecules that are brought up from deeper within Jupiter's atmosphere. This distinct coloring lends it a distinctive, ancient beauty. The winds within the Great Red Spot reach phenomenal speeds, sometimes exceeding 400 kilometers per hour at its edges. But from our distant perspective, its overall rotation appears as a slow, majestic gyre, a timeless witness to the planet's turbulent yet profoundly stable atmospheric processes. It is a powerful, yet serene, testament to the enduring energy and dynamics within Jupiter's deep, fluid atmosphere, a cosmic eye observing the eons. Beyond the Great Red Spot, Jupiter's atmosphere is adorned with magnificent, colorful bands that stretch parallel to its equator, encircling the entire planet. These are not static stripes, but vast flowing currents of gas, known as zones and belts, moving at different speeds and in opposite directions. Picture these as colossal, atmospheric conveyor belts, each distinct in its character. The brighter zones are regions of higher, colder, rising gas, where upward convection brings gases to altitudes where ammonia ice crystals condense, forming the striking white or yellowish clouds. The darker belts, conversely, are regions of warmer, sinking gas, where the clouds are lower in altitude and composed of more complex, colored chemical compounds, perhaps sulfur-rich chromophores or other organic molecules, giving them their characteristic brown, orange, and reddish tones. These distinct bands are created by powerful, alternating east-west jet streams, driven by Jupiter's incredibly rapid rotation. It spins on its axis once every 10 hours, and its significant internal heat. Imagine these high-speed winds as colossal, invisible rivers flowing smoothly around the entire planet, effectively separating the rising and sinking air in adjacent bands. Ammonia, methane, and water ice crystals quietly condense at different altitudes and latitudes, painting these bands with a serene palette of white, yellow, orange, and brown hues. It's a beautiful, planetary scale manifestation of chemistry and dynamics in a ceaseless cosmic dance, an ever-changing masterpiece of atmospheric art. The deep atmospheric structure of Jupiter is truly immense and profoundly mysterious. Far below the colorful cloud tops we observe, the pressure and temperature steadily increase to unfathomable levels. As one descends deeper, the visible ammonia ice clouds give way to ammonium hydrosulfide clouds at lower, warmer levels, then to water ice clouds, and eventually to clouds of liquid water itself, if conditions allow. Deeper still, the immense pressure causes hydrogen itself to transition, not just from a gaseous state to a liquid form, but then to an exotic state called liquid metallic hydrogen. In this region, under pressures millions of times greater than Earth's surface, hydrogen atoms are squeezed so tightly that their electrons are no longer bound to individual nuclei, but float freely, creating a conductive, metallic fluid. This deep internal structure, rather than a solid core, is where Jupiter generates much of its own heat. Indeed, Jupiter radiates more heat into space than it receives from the Sun, making it a source of internal energy, much like a very faint, perpetually cooling star. This internal heat, a quiet glow left over from its formation billions of years ago, is a crucial driver of its atmospheric dynamics. Imagine a gentle yet powerful convection current continuously bubbling up from the planet's deep interior, patiently transporting heat outwards through its immense fluid layers. This internal energy fuels the immense cloud motions, the powerful jet streams, and the long-lived storms like the Great Red Spot. It ensures that Jupiter's atmosphere is not solely dependent on solar radiation for its energy, but possesses its own powerful internal engine, contributing to its majestic and ceaseless activity. A quiet internal fire shaping its external beauty. Studying Jupiter's grand swells and deep hydrogen-helium ocean offers profound insights into the physics of giant planets, not just in our solar system, but also for the numerous exoplanet gas giants discovered around other stars. It reveals a universe where atmospheres can be truly planetary in scale, blurring the lines between what is air and what is the body itself. The quiet, powerful forces at play within Jupiter's atmosphere, its ancient storms, and its colorful bands are a mesmerizing testament to the enduring beauty and complex physics of fluid dynamics on a colossal cosmic stage. It's a vision of quiet power, gently swirling through the vastness of space. A magnificent, vibrant painting against the dark canvas of the cosmos, reminding us of the diverse and immense forms that planets can take. As we float further into this vast topic, Saturn's ringed majesty, hazy skies and subtle storms. From the colossal, swirling depths of Jupiter, we now turn our gaze to its closest giant neighbor, Saturn, a world universally adorned with its magnificent, shimmering rings. Saturn presents an atmosphere similar in fundamental composition to Jupiter's, yet it possesses its own distinct, hazy beauty and unique atmospheric wonders. We will gently explore its more subtle cloud bands, its enigmatic hexagonal storm at the pole, and the serene, deep currents that flow beneath its perpetually veiled golden skies, revealing a true masterpiece of cosmic art, a vision of tranquil power. It is a world that truly captures the imagination, not just for its iconic rings, but for the peaceful dynamics of its ethereal atmosphere. Like Jupiter, Saturn is overwhelmingly composed of the lightest elements, hydrogen and helium. Its atmosphere is approximately 96% hydrogen and 3% helium, with trace amounts of methane, ammonia, and water vapor. These are the same primordial gases captured during the solar system's formation, held by Saturn's immense gravity, mirroring the fundamental building blocks of the early universe. However, Saturn is further from the Sun, roughly twice as far as Jupiter, and is also less massive, resulting in a slightly colder and less dense atmosphere overall. This subtle difference in temperature and pressure significantly influences how its atmospheric features appear to us. The overall scale of the planet is also immense, allowing for deep and complex atmospheric dynamics, yet it retains a certain serene quality due to its distance and visual appearance. While Jupiter's colorful bands are often stark and vibrant, a dramatic canvas of reds and whites, Saturn's cloud features tend to be far more subtle, appearing as muted, pastel hues. Imagine a painting where the colors are softly blended, like gentle brushstrokes across a canvas, rather than boldly contrasting. This is because Saturn's cloud tops are colder, allowing a thick, uniform layer of ammonia haze to form high above the main cloud decks. This pervasive haze acts like a gentle, translucent curtain, softly diffusing the sunlight and obscuring the deeper, more colorful weather patterns below from our direct view. We can still discern faint banding, indicating powerful zonal winds, but they lack the sharp, vivid definition seen on Jupiter. It's a veiled beauty, requiring careful observation and sometimes specialized instruments, like those on the Cassini spacecraft, to fully appreciate its nuances. This atmospheric serenity is a hallmark of Saturn's tranquil demeanor. One of Saturn's most truly enigmatic and mesmerizing atmospheric phenomena is the hexagon, a colossal, six-sided storm structure located precisely at its north pole. Imagine a perfect hexagon, each side spanning approximately 13,800 kilometers, or about 8,600 miles, wider than Earth itself. This immense geometric pattern is not merely a cloud shape, it is actually a stable, persistent jet stream, a high-speed ribbon of air flowing around a central polar vortex. The hexagon has been observed for decades by spacecraft like Voyager and Cassini, its sharp, distinct angles appearing to defy the usual fluid dynamics of circular storms. Its precise formation is still a quiet mystery, a topic of serene scientific investigation, believed to arise from the unique way waves propagate within Saturn's deep, rapidly rotating atmosphere, perhaps interacting with convection cells below. It stands as a silent natural wonder, a perfectly formed cosmic geode, a testament to the unexpected beauty that physics can sculpt on a planetary scale. The hazy layers that contribute to Saturn's characteristic veiled appearance extend high into its atmosphere, giving it that soft, diffuse glow. These hazes are primarily composed of complex hydrocarbons, such as acetylene and ethane, which are formed when methane gas in the upper atmosphere is gently broken down by solar ultraviolet radiation. The energetic photons from the sun act like tiny cosmic scissors, breaking apart the methane molecules. The resulting fragments then slowly combine and condense, forming a fine, stratospheric mist that gives Saturn its soft, golden yellowish glow. Picture a perpetual, delicate fog, softly diffusing the sunlight and lending the planet an ethereal, serene quality that makes it seem almost dreamlike. These hazes play a significant role in Saturn's energy balance, absorbing and scattering sunlight, subtly influencing the planet's overall temperature profile and contributing to its cool, majestic ambience. Beneath these hazy skies and subtle cloud bands, immense serene currents flow with astonishing speed. Saturn actually holds the record for the fastest winds in the solar system, with equatorial jet streams reaching speeds of up to 1,800 kilometers per hour, or over 1,100 miles per hour. This is nearly 4 times faster than Jupiter's most intense winds. These powerful winds are driven by a combination of Saturn's rapid rotation. It spins even faster than Jupiter, completing a rotation in just over 10.5 hours, and its significant internal heat. The combination of its rapid spin, which enhances the Coriolis effect, and the deeper atmospheric penetration of its convection cells contributes to these incredible wind speeds. Like Jupiter, Saturn radiates more heat into space than it receives from the Sun, although the excess heat is less pronounced. This quiet, internal heat, a remnant from its formation billions of years ago when the planet was still contracting and radiating gravitational energy, is a crucial driver of its atmospheric dynamics. Imagine this internal warmth slowly rising, creating vast, deep-seated atmospheric currents that stretch thousands of kilometers into the planet's interior. These deep currents contribute to the formation and stability of the zonal winds and the subtle cloud patterns, even influencing the remarkable hexagonal storm. This internal energy source ensures that Saturn's atmosphere is a vibrant dynamic system, not merely a passive recipient of solar warmth, but a world generating its own powerful atmospheric movements, a quiet internal engine shaping its external beauty. Studying Saturn's ringed majesty with its hazy skies and subtle storms allows us to deepen our understanding of gas giant atmospheres. It highlights how seemingly small differences in mass, distance from the sun, and internal heating can lead to profoundly different atmospheric appearances and dynamics, even between worlds of similar composition. Saturn's tranquil beauty, veiled in golden hazes and adorned with its iconic rings, offers a peaceful, captivating example of the elegant complexities that unfold on a truly colossal scale in the quiet expanse of our solar system. It is a masterpiece of cosmic art, silently drifting through the heavens, a continuous source of wonder and calm observation, inviting us to ponder the grand, subtle variations within our own celestial neighborhood. As we drift deeper into our exploration, the icy twins, Uranus and Neptune's methane veils. From the majestic, hazy beauty of Saturn, our journey now stretches further into the serene depths of our solar system, to the distant realms of the icy twins, Uranus and Neptune. These enigmatic worlds hide their deep, cold interiors beneath atmospheres tinged a mesmerizing blue, a color painted by the profound presence of methane. We will gently explore these far-off giants, where faint cloud bands drift silently, and subtle, frigid storms play out their slow, cosmic dramas across vast, dark expanses, evoking a profound sense of quiet mystery and distant beauty. It is a journey to worlds where the sun is but a distant, faint star, and internal processes quietly shape their ethereal atmospheres. Like their larger cousins, Jupiter and Saturn, Uranus and Neptune are primarily composed of hydrogen and helium. These foundational elements form the bulk of their deep gaseous envelopes. However, they are fundamentally different in their internal structure and atmospheric composition due to their much greater distance from the Sun and distinct formation pathways. Their atmospheres contain a significantly higher proportion of ices, which, in this context, refers to heavier volatile compounds such as water, ammonia, and, crucially, methane, existing in forms not necessarily frozen solid like ice cubes, but rather as supercritical fluids or condensing layers deep within. This greater abundance of these heavier elements is why they are often referred to as ice giants rather than gas giants, representing a distinct class of planetary architecture. It is methane that acts as the key component, painting these distant worlds with their characteristic blue coloration. Imagine sunlight with its full spectrum of colors, gently streaming through the vast, deep, and incredibly cold depths of the Uranian and Neptunian atmospheres. While other gases largely scatter or absorb different wavelengths, methane molecules are particularly efficient at absorbing the red and orange wavelengths of visible light. This selective absorption allows the shorter, bluer wavelengths of light to be scattered more effectively back into space, giving these planets their tranquil, azure appearance. Uranus typically appears as softer, pale cyan, like a calm turquoise ocean seen from afar, while Neptune glows with a deeper, more vibrant sapphire blue, like a luminous jewel suspended in the cosmic dark. This subtle chemical interaction, unfolding on an immense scale, creates an exquisite, natural artistry that defines their visual identity. The precise shade of blue on each is also subtly influenced by the presence of high-altitude hazes, which diffuse the light differently. These distant worlds are defined by their incredibly cold temperatures, a testament to their immense distance from our star. Situated billions of kilometers from the Sun, they receive significantly less solar radiation than Earth, or even Jupiter and Saturn. Uranus, with its average cloud-top temperature of around -216 degrees Celsius, -357 degrees Fahrenheit, is actually the coldest planet in our solar system, even colder than Neptune. But these frigid temperatures, many gases that are vapor on warmer planets condense into icy clouds. For instance, methane itself condenses into clouds of ice crystals in their upper atmospheres, similar to how water vapor condenses into clouds on Earth. The atmospheric layers are far colder, and the thermal energy for driving atmospheric processes is sparse, leading to an environment of profound chill and relative stillness in their upper reaches. Consequently, the visible atmospheres of Uranus and Neptune often appear less active and dramatic than those of Jupiter or Saturn. When Voyager 2 made its historic flybys in the 1980s, Uranus initially appeared as a nearly featureless pale blue sphere, almost devoid of visible cloud bands or storms. Imagine a perfectly smooth, tranquil sphere, a picture of cosmic serenity. However, as our observational capabilities have greatly improved, and with the long-term monitoring by the Hubble Space Telescope, subtle features have begun to emerge, revealing a quiet dynamism beneath the calm facade. These include faint, ephemeral cloud bands, often composed of methane ice crystals, which drift silently across their serene faces, appearing and disappearing over seasons. Neptune, though similar in composition, often displays more noticeable, albeit still subtle, atmospheric activity. During the Voyager 2 encounter, Neptune showcased dramatic, dark, transient storm systems, like the colossal Great Dark Spot, which was reminiscent of Jupiter's red spot, but far less enduring. This vortex, about the size of Earth, was flanked by bright methane ice clouds. Other features, like the Scooter, a bright cloud that moved rapidly around the planet, and smaller, dark spots also revealed a more active weather system. These frigid storms manifest as large, oval-shaped vortices, where methane ice clouds are swept up into their circulation, creating visible patterns against the deep blue backdrop. They are slow, majestic dramas, playing out across vast, dark expanses, appearing and fading over months or years, a testament to the planet's internal dynamics rather than strong solar forcing. Deep internal convection is a crucial driver of atmospheric processes on both Uranus and Neptune, particularly for Neptune, which radiates significantly more internal heat than Uranus. While they receive scant warmth from the distant sun, these ice giants generate a quiet heat from their own interiors, a remnant of their formation and ongoing slow gravitational contraction. This internal heat, escaping outwards, creates a thermal gradient that drives atmospheric circulation from deep within. For Neptune, This internal heat source is more pronounced, allowing for more vigorous convection, which brings warmer gases from deeper within the planet upwards towards the visible cloud layers. Imagine these deep convection currents as slow, invisible plumes of warmer, more buoyant fluid rising gently through the immense icy rocky mantle and lower atmosphere. As these gases rise, they create localized regions of uplift and turbulence, which can then condense into the subtle clouds and fuel the frigid storms we observe. This internal energy source is particularly important for Neptune, helping to explain its slightly more active atmosphere compared to Uranus. For Uranus, with its more modest internal heat, it actually radiates very little excess heat. The atmosphere often appears more quiescent, a tranquil, almost dormant giant, patiently awaiting subtle shifts in its deep internal dynamics to stir its visible layers, revealing fleeting changes to patient observers on Earth. Studying the icy twins, Uranus and Neptune, and their methane veils offers a peaceful journey to the outer reaches of our understanding of planetary atmospheres. They represent a distinct class of giants, where ice-forming volatiles play a more prominent role, and where the dance of warmth is dictated less by the sun and more by the quiet glow from within. Their distant, enigmatic beauty and subtle atmospheric activity are a testament to the diverse and complex ways that the fundamental physics of fluids and gases unfold across the vast, serene canvas of the cosmos. These worlds remind us of the incredible range of atmospheric conditions that can exist, even in the coldest, darkest corners of our solar system, each a unique expression of cosmic forces. As we drift deeper into our exploration, Titan's methane mystery, lakes, rivers, and a nitrogen sky, we have journeyed to the colossal ice giants, Uranus and Neptune, witnessing their distant, frigid beauty. Now, our exploration takes us to an even more exotic and deeply fascinating world, Titan, Saturn's largest moon. Titan is unique in our solar system, enveloped in a thick, nitrogen-rich atmosphere, a place where liquid methane and ethane form serene lakes and rivers. This deeply familiar, yet utterly alien landscape, shrouded in a gentle orange haze, invites us to ponder a world where the water cycle is replaced by a methane cycle, a peaceful, shimmering mirror of Earth in a cosmic deep freeze. It truly offers a profound blend of the familiar and the fantastically foreign, a cosmic dreamscape. The most striking feature of Titan, one that sets it apart from almost every other moon, is its incredibly thick atmosphere. Imagine an atmosphere so substantial that its surface pressure is about 50% higher than Earth's, comparable to the pressure you would feel if you were just a few meters underwater here on Earth. This dense, pervasive envelope is overwhelmingly dominated by nitrogen, making up over 95% of its composition, with methane constituting the other few percent, along with trace amounts of other complex hydrocarbons. This nitrogen-rich atmosphere is remarkably similar in its primary composition to the early atmosphere of Earth, billions of years ago, before life profoundly altered its makeup. This quiet parallel to our own distant past offers a profound sense of cosmic connection, inviting us to reflect on our own planet's ancient history through the lens of another world. But the true mystery and wonder of Titan lie in its active methane cycle. Picture a hydrological cycle on Earth with evaporation, clouds, rain, rivers and lakes, but replace water with liquid methane and ethane. On Titan, temperatures are incredibly cold, averaging around -179 degrees Celsius or -290 degrees Fahrenheit. At these frigid temperatures, methane exists naturally in all three phases, as a gas in the atmosphere, as a solid in the form of ice on the surface, which is essentially rock hard at these temperatures, and crucially, as a liquid, forming vast serene lakes and winding rivers across its frigid landscape. This unique thermodynamic state makes Titan a truly special place in our solar system. Imagine the Cassini spacecraft's radar gently piercing through the obscuring haze, revealing vast, smooth, dark patches across Titan's polar regions. These are not solid ground, but tranquil, mirror-like lakes and seas of liquid methane and ethane. Scientists have meticulously mapped these liquid bodies, some as large as North America's Great Lakes, with evocative poetic names like Kraken Mare and Ligeia Mare. From these vast liquid bodies, methane gently evaporates, rising into the atmosphere to form clouds. When these clouds reach saturation, methane quietly condenses and falls as rain, replenishing the rivers and lakes below. The Huygens probe, which famously landed on Titan in 2005, captured breathtaking images of what appeared to be dried-up riverbeds, carved by ancient flows of liquid methane and ethane, snaking across the landscape, a testament to this active, alien hydrology. It is a slow, quiet, continuous cycle, a truly breathtaking example of fluid dynamics in a deeply alien yet eerily familiar setting, inviting peaceful contemplation of geological processes on cosmic scales. Titan's sky is not blue like Earth's. Instead, it is permanently shrouded in a gentle, pervasive organic haze, giving it a soft, diffuse orange glow that extends for hundreds of kilometers above the surface. This haze effectively obscures the moon's surface features from direct visible light observation from space, creating a perpetual twilight at ground level. Imagine gazing up at a perpetual sunset sky, a continuous muted glow that bathes the entire world. These haze layers are formed when methane and nitrogen molecules in the upper atmosphere are gently broken apart by ultraviolet radiation from the sun and energetic particles from Saturn's vast magnetosphere. The resulting fragments then quietly recombine into more complex hydrocarbon molecules, such as acetylene, ethane, and even more complex tholins, forming tiny solid particles, or aerosols, that aggregate and fall slowly through the atmosphere. These organic particles are what create the characteristic orange hue and contribute to Titan's thick, insulating atmospheric blanket. This constant production of complex organic molecules in Titan's upper atmosphere is a source of immense scientific interest, as these are the very building blocks of life, gently forming in a frigid, alien chemical laboratory. But where does all this methane come from? In a process reminiscent of Earth's geology, Titan replenishes its atmospheric gases through what we call cryovolcanism. Unlike the fiery eruptions of molten rock on Earth, cryovolcanoes on Titan erupt with a slushy mixture of water ice, ammonia, and methane, often in liquid or vapor form, from beneath the moon's icy crust. Imagine a gentle, slow ooze of icy lava, or a quiet plume of gas and solid particles, silently replenishing the atmosphere from cracks and fissures in the moon's icy crust. This internal geological activity, driven by subsurface heat, ensures a continuous supply of methane to the atmosphere, compensating for its slow loss to space and its conversion into ethane through photochemical reactions. It is a subtle, yet powerful, connection between Titan's deep interior and its dynamic active surface and atmosphere, a silent engine driving its unique chemistry and sustained by tidal heating from Saturn. Titan is, in many profound ways, a peaceful mirror of early Earth, albeit one frozen in time and operating with profoundly different chemical components. It provides a unique natural laboratory for studying prebiotic chemistry, the complex chemical processes that are thought to have occurred on Earth before the advent of life, giving rise to its first biological molecules. The abundance of complex organic molecules, the liquid environments, and the thick protective atmosphere make Titan a prime target for future exploration, with ambitious missions like NASA's Dragonfly, a rotorcraft lander, planned to gently explore its surface and atmosphere, quietly seeking to understand its organic richness. So, Titan's methane mystery, with its serene lakes, winding rivers, and nitrogen sky veiled in orange haze, stands as a profound testament to the diverse and wondrous ways that fundamental physical and chemical laws can manifest across the cosmos. It invites us to quietly contemplate a world both familiar and alien, a place where the familiar cycles of nature play out with entirely different ingredients and at vastly different temperatures. It is a deeply engaging and peacefully inspiring example of planetary physics in action, offering a unique window into the rich possibilities of planetary evolution beyond our own blue marble. Our journey through space now brings us to Io's volcanic plumes, a sulphurous breath. From the serene, methane-rich atmosphere of Titan, our journey now takes us to a dramatically different kind of world, one born of fiery internal heat and constant violent exhalation. We journey to Io, the innermost of Jupiter's 4 largest moons, a place where we witness an atmosphere born almost entirely of intense, ceaseless volcanic activity. Here, vast plumes of sulfur dioxide silently erupt into its thin air, creating a constantly renewing, vibrant environment. It is a world of dramatic geological processes, yet we observe it from a distant, peaceful perspective, marveling at its unique sulphurous breath. Io is arguably the most volcanically active body in our entire solar system. Its intense internal heat, which powers this ceaseless volcanism, comes from a remarkable phenomenon called tidal heating. Imagine Io being constantly squeezed and stretched by the immense gravitational forces of Jupiter and its other large moons, Europa and Ganymede, as it orbits its giant parent. This continuous gravitational tug-of-war generates tremendous friction deep within Io's interior, melting rock and creating vast reservoirs of magma. This internal churning results in hundreds of volcanoes across its surface, many of which are continuously erupting, painting the moon's surface in vivid shades of yellow, orange and red, all caused by various sulfur compounds. It is this intense volcanism that serves as the primary and almost sole source of Io's thin, transient atmosphere. Unlike Earth, where gases were outgassed once and then gradually evolved, Io's atmosphere is in a constant state of violent creation and swift destruction. Picture a multitude of volcanic vents, gently yet persistently, belching out gases and tiny particles into the near vacuum of space. These plumes are the lifeblood of Io's atmospheric presence, silently replenishing it even as it constantly escapes. The main atmospheric component of Io's tenuous envelope is sulfur dioxide, often abbreviated as SO2. When these volcanic plumes erupt, they carry sulfur dioxide gas and tiny particles of sulfur compounds high above the surface, sometimes hundreds of kilometers into space. This SO2 gas then spreads out, forming an incredibly thin, diffuse atmosphere that envelops the moon. While there are also trace amounts of sulfur monoxide and atomic oxygen, it is the sulfur dioxide that dominates this sulphurous breath. Its presence is directly tied to the moon's fiery internal engine, making its atmosphere a direct manifestation of its geology. Io's atmosphere is in a state of rapid renewal and constant escape. Imagine a leaky bucket constantly being refilled by a powerful stream of water. The volcanic plumes act as the continuous refill, but Io's relatively weak gravity and its constant exposure to Jupiter's harsh radiation environment mean that gas molecules are continuously lost to space. A molecule of sulfur dioxide might only last for a few hours in Io's atmosphere before it either freezes back onto the extremely cold surface, particularly on the night side, or gains enough energy to escape into Jupiter's magnetosphere. This extremely short atmospheric lifetime makes it a truly dynamic and transient gaseous veil. The rate at which gases are volcanically ejected is roughly balanced by the rate at which they escape, creating a thin but perpetually present atmosphere. The density of Io's atmosphere can also vary significantly. For instance, when Io passes into Jupiter's shadow, shielded from direct sunlight, temperatures drop dramatically. This causes a significant portion of the sulfur dioxide atmosphere to freeze out onto the surface as a frost, temporarily thinning the atmosphere even further. When it emerges back into sunlight, the SO2 sublimates, replenishing the gaseous envelope. It's a silent daily breathing of the moon, driven by solar heating and extreme cold. Crucially, Io's atmosphere and its volcanic output are profoundly influenced by its interaction with Jupiter's incredibly strong magnetic field. Jupiter possesses the most powerful magnetic field of any planet in our solar system, creating a vast magnetosphere that stretches millions of kilometers. Io orbits deep within this magnetosphere, acting like an immense electrical generator as it carves through Jupiter's magnetic field lines. This interaction generates a tremendous electrical current, estimated at millions of amperes, that flows between Io and Jupiter, creating what we call the Io flux tube. This powerful electrical interaction has several profound effects. Firstly, it enhances the atmospheric escape from Io. As Io moves through the magnetosphere, charged particles from Jupiter's environment gently yet forcefully bombard Io's upper atmosphere, knocking off atoms and ions and sweeping them away into a donut-shaped cloud of plasma that surrounds Jupiter, known as the Io plasma torus. Imagine a silent cosmic wind continuously stripping away tiny fragments of Io's breath. Secondly, the energy generated by the Io flux tube also contributes to the tidal heating within Io's interior. This is a complex interplay, where the electromagnetic forces enhance the very gravitational forces that cause the intense volcanism, creating a powerful feedback loop that drives Io's fiery heart. This intricate dance between gravity, electromagnetism, and internal geology makes Io's atmosphere one of the most uniquely generated and dynamic in our solar system. Studying Io's volcanic plumes and its sulfurous breath offers us a distant, peaceful window into the extreme end of atmospheric formation. It showcases a world where the atmosphere is not a stable blanket, but a continuous, violent exhalation from a constantly churning interior, exquisitely tuned by powerful tidal forces and a dominant magnetic field. It is a world of dramatic, yet constant renewal, a vibrant testament to the incredible range of atmospheric processes that quietly unfold across the vast and diverse tapestry of the cosmos. This fiery moon, perpetually breathing out its sulfurous air, reminds us that even in the most extreme environments, fundamental physics orchestrates a captivating, ceaseless drama. Our journey through space now brings us to Triton's whispers, nitrogen ice and cryovolcanic geysers. From the fiery exhalations of Io, we now journey to another moon, one that whispers with an even more tenuous breath, residing in the coldest, outermost reaches of our solar system, Triton. Neptune's largest moon, Triton, is a world of nitrogen ice and enigmatic cryovolcanic geysers. Here, faint plumes of sublimating ice silently erupt into a thin nitrogen atmosphere. We will explore this intensely cold, distant world, marveling at its unique features and the quiet, ethereal processes that shape its icy, beautiful surface and its thin, gently escaping veil of gas, a profound testament to cold, slow cosmic artistry. Triton is a truly frigid realm, boasting the coldest surface temperatures of any known body in our solar system, plummeting to an astonishing -240 degrees Celsius, or -400 degrees Fahrenheit. At these extreme temperatures, gases like nitrogen and methane, which are atmospheric components on Earth and Titan, exist as hard, stable ices on Triton's surface. Yet, even in this profound cold, Triton manages to retain a whisper of an atmosphere, composed primarily of nitrogen, with trace amounts of methane and carbon monoxide. It is incredibly thin, about 70,000 times less dense than Earth's atmosphere at sea level, making it closer to a vacuum than to a breathable environment. This tenuous nitrogen atmosphere is thought to arise mainly from the sublimation of nitrogen ice directly from Triton's surface. Imagine the faint, distant sunlight from the sun, now just a bright star, gently warming patches of nitrogen ice. This subtle warmth is enough to cause some of the solid nitrogen to bypass the liquid phase entirely and turn directly into gas, rising gently to form the atmosphere. This process is highly seasonal, meaning the atmospheric pressure and density fluctuate as different parts of Triton's surface are exposed to more sunlight over its long, complex orbit around Neptune. It's a silent, slow respiration, a continuous exchange between the solid surface and the gaseous envelope. One of Triton's most unexpected and captivating features, discovered by Voyager 2 during its fleeting 1989 flyby, are its cryovolcanic plumes. Picture dark, faint streaks extending high above Triton's surface, reaching up to 8 kilometers or 5 miles, before being gently swept away by high-altitude winds. These are not fiery eruptions of molten rock, like on Io, but silent, ethereal geysers of nitrogen gas and dark dust particles. Scientists believe these plumes are formed by the sun's faint warmth slowly heating a layer of nitrogen ice beneath the surface, transforming it into pressurized gas. This gas then finds cracks or vents and quietly erupts upwards, carrying along dark, organic dust particles from below the ice. Imagine a slow, cold eruption, like a quiet sigh from the moon's interior. These cryovolcanic plumes are a unique form of geological activity, directly feeding material into Triton's sparse atmosphere and leaving dark streaks on its bright, icy surface, like fleeting brushstrokes on a frozen canvas. They speak of a subtle, internal dynamism, even in such a cold, distant world. Triton's retrograde orbit, meaning it orbits Neptune in the opposite direction to Neptune's rotation, is a crucial influence on its evolution and atmospheric characteristics. This unusual orbit strongly suggests that Triton was not formed with Neptune, but was rather a dwarf planet from the Kuiper Belt, gently captured by Neptune's gravity long ago. This capture event would have been immensely energetic, generating enormous tidal forces that would have violently reshaped Triton's interior, providing an initial burst of heat. This primordial heat could have driven early geological activity, resurfacing the Moon and perhaps establishing the initial conditions for its current cryovolcanism and atmospheric outgassing. The ongoing tidal interactions, though less extreme now, still contribute to Triton's internal energy, subtly influencing its deep thermal state and allowing for the continuous, quiet processes that replenish its atmosphere and drive its geysers. It is a slow, elegant dance of captured gravity and internal response, continuously shaping this distant, icy world. The thin, escaping veil of gas on Triton is a testament to the challenges of holding on to an atmosphere in such an extreme environment. With weak gravity and intense cold, any gases that manage to sublimate or erupt from the interior are always on the verge of escape. The upper reaches of Triton's atmosphere gradually blend into the vacuum of space, with gas molecules slowly drifting away, a continuous, quiet loss to the cosmic void. Yet, the persistent activity of the cryovolcanic geysers and the seasonal sublimation of nitrogen ice ensure that Triton's whisper of an atmosphere remains, a testament to the fragile yet enduring presence of gas even in the most inhospitable corners of our solar system. Studying Triton, its tenuous nitrogen atmosphere, and its silent cryovolcanic geysers offers a peaceful, profound understanding of planetary processes at the extreme edges of our solar system. It reveals a world of subtle yet powerful activity, a cold, distant beauty that quietly challenges our assumptions about what constitutes an active atmosphere. This icy moon, patiently unfolding its geological and atmospheric story, reminds us of the incredible diversity and quiet dynamism found throughout the vast, serene tapestry of the cosmos, even in the deepest freeze. Continuing our peaceful voyage through the universe, beyond our solar system, detecting exoplanet atmospheres, we have journeyed across our solar system, from the fiery embrace of Venus to the frigid whispers of Triton, exploring the incredible diversity of atmospheres around planets and moons. Now, our quest extends even further, beyond the familiar bounds of our sun's domain, to the countless exoplanets orbiting distant stars. Our journey now gently concludes by casting our gaze into this vast, largely unknown territory. We will explore how astronomers, through subtle cosmic signals, can patiently detect and even analyze the atmospheres of these faraway worlds, searching for the quiet whispers of chemical compositions that might hint at life, a profound and peaceful quest into the cosmic unknown. Detecting an exoplanet is itself a remarkable feat, given the immense distances involved. But detecting and analyzing its atmosphere, a faint veil of gas around a tiny, distant world, is an even more astonishing accomplishment, akin to deciphering a whispered message across an infinite expanse. The primary method for this delicate task is known as transit spectroscopy. Imagine a distant exoplanet gracefully passing directly in front of its host star from our perspective, an event called a transit. As the exoplanet moves across the star's face, the starlight we receive momentarily dims. But as the planet's atmosphere subtly filters the starlight, certain wavelengths of light are absorbed by the gases present in that atmosphere. Different gases absorb different colors or wavelengths of light, creating a unique chemical fingerprint. Astronomers use powerful telescopes, both on Earth and in space, to carefully observe the starlight during a transit. By comparing the light that passes through the exoplanet's atmosphere to the light that doesn't, they can detect these subtle absorption features. It's like gently holding a thin, colored filter up to a bright light and seeing which colors are diminished. This allows us to infer the atmospheric composition, revealing the presence of elements like hydrogen, helium, sodium, potassium, water vapor, and even methane and carbon dioxide in these faraway worlds. This patient, spectroscopic analysis is a true testament to human ingenuity and our ability to extract profound information from the faintest cosmic signals. Another, more challenging, method for detecting exoplanet atmospheres is direct imaging. Imagine trying to see a firefly hovering next to a searchlight from thousands of miles away. Stars are immensely bright, utterly overwhelming the faint glow of their orbiting planets. However, with advanced instruments that block out the dazzling starlight, scientists can sometimes directly image the light reflected or emitted by a very few, very large and often young exoplanets. Analyzing the light from these directly imaged planets can then reveal the composition of their atmospheres. This technique is like gently separating the faint shimmer of a distant dewdrop from the blinding glare of its sun, requiring incredible precision and patience. From this analysis of light, we can infer the atmospheric composition, which tells us much about the exoplanet's nature. For instance, finding large amounts of hydrogen and helium might indicate a gas giant similar to Jupiter. Detecting water vapor could suggest a world where conditions for liquid water might exist. Even the presence of haze layers, similar to Titan's, can be inferred from how much light is scattered at different wavelengths, providing subtle clues to a planet's atmospheric structure and chemistry. It is a quiet, intellectual detective story, piecing together the invisible elements of distant worlds. Perhaps the most profound aspect of this exoplanet atmospheric research is the search for biosignatures, gases indicative of life. On Earth, as we discussed, the abundant oxygen and methane in our atmosphere are constantly being produced by biological processes. Without life, these reactive gases would quickly disappear due to chemical reactions. So, finding a planet with, for example, significant amounts of both oxygen and methane in its atmosphere, in a state of chemical disequilibrium, would be a compelling, though not definitive, whisper of life. It would suggest an active, thriving biology continually replenishing these gases. Imagine the quiet excitement of such a discovery, detecting the faint breath of life across light years. These are the ultimate scientific prizes, the gentle echoes of biology reaching us from across the vastness. Future telescopes, like the James Webb Space Telescope, are exquisitely designed to precisely measure these atmospheric fingerprints, pushing the boundaries of what we can quietly observe. This vastness of the exoplanet search is truly humbling and inspiring. Thousands of exoplanets have already been discovered, and with each new detection, our understanding of planetary diversity grows exponentially. From hot Jupiters, orbiting scorching close to their stars, to super-Earths in potentially habitable zones, each discovery reveals new atmospheric chemistries and dynamics. We are just beginning this gentle exploration, peering through the cosmic veil to see the subtle light of other worlds and listen for the quiet stories their atmospheres tell. Our journey concludes with this profound quest, a patient and peaceful search for understanding that stretches across the universe. The ability to detect and characterize exoplanet atmospheres is a monumental leap, transforming our understanding of planetary possibilities and bringing us closer to answering one of humanity's oldest, most peaceful questions. Are we truly alone in this magnificent, silent cosmos? This ongoing scientific endeavor, observing the subtle interactions of light and gas from unimaginable distances, leaves us with a sense of calm wonder and boundless anticipation for the discoveries yet to gently unfold. As we float further into this vast topic, the silent storytellers, what atmospheres reveal about a world? We have journeyed far and wide, exploring the diverse and wondrous atmospheres that embrace worlds both near and unimaginably distant. As we gently reflect on this cosmic tapestry, a profound realization emerges. Every atmosphere tells a silent story. From its intricate composition to its serene layers, its delicate temperature balance to its sweeping winds, an atmosphere whispers tales of a world's turbulent formation, its long geological history, its elegant orbital dance, and even its deep potential for life. Atmospheres are the gentle chroniclers of cosmic time, offering profound, peaceful insights into the universe's grand and intricate design. Consider, for a moment, how atmospheres act as subtle indicators of a planet's deep planetary geology and its internal heat. The presence of certain gases, even in trace amounts, can point to active processes hidden beneath the surface. On Earth, our volcanic outgassing contributes to gases like carbon dioxide and water vapor, linking our atmosphere to the slow churn of our mantle. But on Io, the incredibly active volcanism directly, dramatically, and constantly replenishes its sulfur dioxide atmosphere, making its very breath a direct manifestation of its immense tidal heating and molten interior. Similarly, the hazy, organic, rich atmosphere of Titan, though cold, is gently sustained by cryovolcanism, hinting at a subsurface ocean of liquid water and ammonia, warmed by internal processes. Even the subtle variations in the blue hues of Uranus and Neptune reveal the quiet interplay of their deep internal heat with their atmospheric methane, influencing the visibility and dynamics of their cloud layers. An atmosphere, then, is a planetary window, softly hinting at the powerful hidden engines that drive a world from within, a gentle echo of its internal pulse. Furthermore, atmospheres serve as eloquent clues about a planet's formation and its long, patient evolutionary journey. The atmospheres of the gas giants, Jupiter and Saturn, overwhelmingly composed of primordial hydrogen and helium, speak of their direct capture of material from the solar nebula, preserving the very ancient building blocks of our system. They are living fossils of cosmic birth, their deep gaseous oceans largely unchanged since the dawn of our sun. Conversely, the secondary atmospheres of rocky planets like Earth, Venus and Mars, formed through outgassing from their interiors, tell a different tale. Mars's thin carbon dioxide atmosphere, with its evidence of past liquid water, recounts a history of atmospheric loss, a slow erosion by the solar wind after its magnetic field waned. Venus's dense, scorching carbon dioxide veil narrates a dramatic runaway greenhouse effect, a planetary climate shift so profound that it utterly transformed the world. Each atmospheric profile is a chapter in a cosmic biography, patiently detailing billions of years of formation, change, and destiny. Perhaps most compellingly, atmospheric composition is a fundamental key to understanding planetary habitability. We have seen how Earth's unique harmony of nitrogen, abundant oxygen, and the dynamic water cycle creates the stable, temperate conditions necessary for life. This delicate balance, maintained by the natural greenhouse effect and protected by the ozone layer, is a rare cosmic gift. The presence of liquid water, both on a planet's surface and cycling through its atmosphere, is often considered the most crucial ingredient for life as we know it. When we observe distant exoplanets, searching for biosignatures, we are looking for atmospheric compositions that are out of chemical equilibrium, such as the simultaneous presence of oxygen and methane. Such a finding would be the quietest, yet most profound, whisper that an active, living biosphere is at work, continually altering its planet's air. These atmospheric ingredients are not merely passive elements, they are vital, active participants in the grand, peaceful drama of life's emergence and sustenance. Ultimately, these atmospheric stories highlight the profound interrelationship of planetary systems. An atmosphere is not an isolated phenomenon. It is intimately connected to a planet's gravity, its internal heat, its geological activity, its distance from its star, its magnetic field, and even the presence of life itself. Each component influences the others, creating a complex yet beautifully balanced planetary whole. The atmospheric circulation, the dance of warmth, the subtle scattering of light. All these processes are interwoven, creating the unique weather, climate, and appearance of each world. Imagine a vast, intricate clockwork mechanism, where each tiny gear and spring, each atmospheric variable, precisely influences the movement of the whole. This holistic view reveals the profound elegance and quiet order that underlies the diversity of worlds in our cosmos. As we conclude this reflection, we are left with a deeper sense of calm wonder and intellectual satisfaction. The study of planetary atmospheres is more than just observing clouds and gases. It is about listening to the silent stories these cosmic envelopes tell, deciphering the profound physics that govern them, and understanding their intimate connection to the life that may or may not thrive beneath their embrace. Atmospheres are not merely blankets of air. They are the vibrant, dynamic, and ever-evolving expressions of planetary identity, offering endless, peaceful insights into the universe's grand design and our own humble place within it. Our journey through space now brings us to our ongoing journey, the future of atmospheric exploration. We have gently navigated the profound stories that atmospheres tell, deciphering the silent chronicles of cosmic time etched into their very fabric. As our expansive journey through the physics of planetary atmospheres draws to a close, it is important to remember that our quest to understand these ethereal blankets is an ongoing, peaceful voyage of discovery. The dedicated curiosity of scientists, fueled by innovative missions and powerful new telescopes, continues to unveil secrets, quietly pushing the boundaries of our knowledge. This quiet exploration promises even deeper understandings and new wonders, a never-ending journey into the cosmic unknown. The future of atmospheric exploration is bright, filled with a sense of calm anticipation. New missions are always being planned, designed to delve deeper into the atmospheric mysteries of our solar system. Consider, for instance, NASA's Dragonfly mission, a rotorcraft lander currently being built, destined for Saturn's enigmatic moon Titan. Imagine this graceful drone gently flying through Titan's dense, nitrogen-rich atmosphere, powered by nuclear energy, quietly exploring its organic hazes, sampling its surface, and even flying over its methane lakes. Dragonfly will offer unprecedented in-situ measurements of Titan's atmospheric chemistry and dynamics, revealing insights into a world where an alien form of the water cycle plays out with entirely different fluids. It is a peaceful leap into an entirely new mode of planetary exploration. Another exciting prospect is the Veritas mission to Venus, a concept currently under consideration. If selected, Veritas would quietly orbit Venus, using radar to pierce through its thick fiery veil of carbon dioxide, mapping its surface and peering into its deep atmospheric structure. Such a mission would provide crucial data to understand how Venus evolved to its current state, offering profound insights into the runaway greenhouse effect and the potential for past oceans and atmospheres. It would be a patient, meticulous effort to unravel the secrets of our closest planetary neighbor, a world that holds so many lessons about climate evolution. Beyond our solar system, next-generation telescopes are profoundly transforming our ability to study exoplanet atmospheres. The recently launched James Webb Space Telescope, or JWST, is a true marvel of engineering, quietly observing the universe in infrared light. Imagine its colossal golden mirror, patiently gathering the faint light from distant stars, searching for the subtle fingerprints of gases in the atmospheres of exoplanets as they transit their host stars. JWST is exquisitely sensitive to water vapor, methane, carbon dioxide, and other key molecules, allowing us to build up a detailed chemical profile of these faraway worlds. It is providing unprecedented insights into the diversity of exoplanet atmospheres, quietly reshaping our understanding of planetary formation and evolution beyond our own cosmic neighborhood. Looking even further ahead, missions like the Nancy Grace Roman Space Telescope, currently under development, will continue to advance our capabilities. While Roman will focus on wide-field surveys and dark energy, its advanced coronagraph technology may one day pave the way for future telescopes designed to directly image Earth-sized exoplanets and analyze their atmospheres. Imagine a future where we can calmly observe a faint blue dot many light-years away and confidently identify the chemical composition of its air, searching for those whispers of life. This continued scientific inquiry and discovery is a testament to humanity's innate curiosity, a peaceful and boundless drive to understand our place in the cosmos. Each new mission, each data point from a distant telescope, adds another gentle brushstroke to our ever-expanding portrait of the universe. The insights we gain are not just about the physics of gases. They are about understanding the fundamental processes that govern worlds, the delicate balances that allow for habitability, and the conditions under which life might emerge and thrive. The promise of future insights into planetary habitability and the potential for life beyond Earth is perhaps the most profound aspect of this ongoing journey. By studying the atmospheres of exoplanets, we seek to answer one of humanity's most enduring and peaceful questions. Are we alone? Discovering an atmosphere with the right combination of biosignature gases would be a monumental step, a quiet revolution in our understanding of life's place in the universe. It would change our cosmic perspective forever, fostering an even deeper sense of connection to the vast living cosmos. So, as we bring our tranquil exploration to a close, let us carry forward this sense of calm wonder and anticipation. The universe is immense, filled with endless mysteries, and the atmospheres that embrace its worlds are some of its most eloquent storytellers. Our journey to understand them is far from over. It is a continuous, peaceful voyage into the unknown, a testament to the quiet power of scientific curiosity, endlessly unfolding new wonders with each gentle turn of the cosmic page. May this knowledge bring you a peaceful sense of connection to the grand design of the universe as you drift into quiet contemplation. As our cosmic journey through the physics of planetary atmospheres, from Venus's greenhouse to Titan's methane lakes, draws to a peaceful close, take a moment to let these wonders settle in your mind like stardust drifting through space. From the smallest particles to the grandest cosmic structures, everything we've explored tonight is part of the same magnificent universe that cradles our small blue planet. As you drift off to sleep, remember that you are made of star stuff, connected to every distant galaxy and cosmic phenomenon we've discussed. The universe is vast, beautiful, and filled with endless mysteries waiting to be discovered. But for now, rest well, knowing that tomorrow the cosmos will still be there, patiently waiting for curious minds like yours to explore its secrets. Sweet dreams, fellow space travelers.